so today's session, session 3, is discussing planets and life. Our first talk today is going to be given by Jessie Christiansen, who will be discussing exoplanets in the Milky Way, results from Kepler.
Hi everyone, good morning. I know it's early. I've got to get through 4,000 exoplanets in about 30 minutes, so we'll see how far we get. The topic I was given to talk about was exoplanets in the Milky Way, subtitled Results from Kepler, and I will talk a lot about Kepler, but I didn't want to exclude the 1,700 or so planets that weren't found by Kepler, so there'll be some of those in there too. Okay, so this was the distribution of exoplanets we knew before the launch of Kepler. So what I'm showing here is the orbital period of the planet on the x-axis and the size of the planet relative to Earth on the y-axis. So Earth is here, Neptune is here, and Jupiter is here at 11. So this is in days, and it's a log scale, so 365 days, 1 Earth radius. These are the inner solar system planets. So we knew about those ones. That's Mercury, Venus, Earth, and Mars. So these are the exoplanets we knew about. You can see most of them were this new class of planet that we discovered when we started finding exoplanets called hot Jupiters. Up here, hot Jupiters were not very imaginative. They're just Jupiters that are thousands of degrees, so great. And then Kepler launched, and I'll talk a little bit more about that. But this was the picture after Kepler. You can see we've actually done a really good job of filling in the space between what we knew before, the hot Jupiters, and what we knew, the inner solar system, with this whole mess of stuff. So we've learned a lot about the exoplanets that surround us in the Milky Way. And I guess if you take home one message from the talk, it's 9 a.m., I'll just give you something really digestible. Exoplanets are very common. It seems like exoplanets are everywhere in the galaxy. Everywhere we look, we find them. So that's exciting. That's your one take-home point. Now we'll get into the nitty-gritty. Okay, so the NASA Kepler mission launched in 2009. It's a 1-meter telescope. It had 2 phases. The original mission ran from 2009 to 2013 when 2 of its 4 reaction wheels broke and it wasn't able to keep doing its original mission. Its original point was to stare at a single patch of sky about 10 degrees by 10 degrees in the constellation Cygnus and to answer primarily one question: how common are planets like the Earth? And that sentence, I know this room full of people, that sentence already has so many pitfalls in it. What does planets like the Earth mean? What do we mean when we say that? So for Kepler, we wanted rocky planets, so planets with a density close to rock, not volatile rich or gas rich, rocky planets with a surface you could stand on, that were, and I'm being followed by a talk about the habitable zone, so I'm not going to get into that too much, but that were within temperatures of 180 to 303 degrees Kelvin, and orbiting stars like the Sun. That's the 3 criteria for Earth-like, according to Kepler. And orbiting stars like the Sun becomes important later in the talk. But that's what we were aiming for. How common are planets like that? After the 2 reaction wheels failed, it went into its second phase, the K2 mission, which ran for 4 years after that. That was a survey of the ecliptic plane, since that's the only place we could point reliably with 2 reaction wheels. And that all has also found hundreds of planets, not quite the thousands found by the original Kepler mission, but hundreds of planets, and was an amazing success given the engineering failures. They overcame these reaction wheels failures and running out of fuel, and they eked every microgram of hydrazine out of the spacecraft to push it as long as they did. By the end, the fuel readers couldn't even read how much fuel there was because they were designed to read pressure in the tank, and there was no pressure in the tank anymore. They were running on the vapor in the lines between the tank and the thrusters. So they got every single second they could. Okay, so as I said, it's a 1-meter telescope, so this is actually kind of the size of a small school bus. It was a 100 square degree field of view, and in that field of view, we looked at 200,000 stars, moderately bright, moderately faint, depending on how you like your magnitudes, brighter than 16th magnitude. The majority were between 14th and 16th magnitude, and we surveyed them every 30 minutes. So every 30 minutes, we just took a picture of that patch of sky over and over again for 4 years. Why were we doing that? Because Kepler uses the transit method to discover planets. There's a bunch of different ways, about 10 now, that we've managed to use to find exoplanets. In the last 25 years, we've gone from 0 to 10. I'm only really going to talk about the transit method. I think Jason Wright's going to talk about the RV method later, and Angie might touch on microlensing. But the transit method is the one that has found the most of the planets. Okay, so this is our sun and that is a transit of Mercury. So this is an old video, but there's actually another transit of Mercury happening later this year, so November, I think. So keep your eyes out for that. I'm really excited because transit method is how we find planets, and now we get to find Mercury again. We get to rediscover Mercury. So when Mercury comes in front of the sun, it blocks some of the light, right? You can see it's actually literally occulting some of the star. So what we do is we measure the brightness of the stars over and over again, and as the planets come around and block the light, you measure these little dips over and over again, periodically these little dips. So Mercury actually blocks very little of the light, 0.002%. That's not a lot. Earth, if Earth transited, if you're an alien civilization many light years away and we're angled just right, you would see Earth transit and it would block 100 parts per million, 0.01% of the light, which is still a tough measurement to make, and that's why we actually had to go to space. But then Earth isn't the only planet in the solar system. Jupiter actually comes along and blocks 1% of the light. So 1% is actually something we can do from the ground. We can do 1% photometry from the ground. We can do better than 1% photometry from the ground now. But that's, you can see why Jupiters were found first, because they block, they make a bigger signal. And the hot Jupiters transit every 2 or 3 days, so you get many chances to see these transits. So this is the transit method. Kepler used this, stared at that field for 4 years. Okay, and what did it uncover? So again, I'm kind of lumping Kepler in with all of the rest of the planets that are, not all of these were found by Kepler, but Kepler did contribute this largest set. So the hot Jupiters, we'll talk a little bit about. We found many ocean worlds and ice giants, which I won't touch on too much, but they were exciting to find. These are all still quite warm, so again, Earth is here. So these are all planets interior to the orbit of Earth. So this warm Neptune is this new class of planet we've been investigating as much as we can, because that's really interesting. Lava worlds is another group that we found. So these are Earth-sized planets, so rocky, orbiting in less than a day from their star. So one of the talks yesterday was, how can you make a magma ocean? Well, you can take your rock and you can put it right next to the star, and then it will be so hot that the surface will melt. So we actually do have lava worlds, which is pretty cool. And then we did find many rocky planets, which I'll talk more about. But interestingly, the bulk of the planets that we found between Neptune and Earth are a mystery. We're still learning this. We don't have any planets in our solar system between the size of Earth and Neptune. So there's this whole huge population of planets that are kind of a mystery to us that we're exploring right now. Okay, so I said that the goal of Kepler was to find out how common planets like the Earth are. And unless you want an upper limit, then you need to find some planets like the Earth. Did we find any planets like the Earth? Maybe. This is Kepler 452b. So it is orbiting a star like the Sun. Check. It is in the right, it's the right distance. It's got a period of about 380 days, which is very similar to our 365. So it's at the right temperature range. Check. It's a little big, so it's about 1.5 times the radius of the Earth compared to 1, and that's about where we think that things transition from being predominantly rocky to volatile, rich, more like mini Neptunes. I should pause and say, one of the problems with the planets that Kepler found is most of them can't be followed up. They're very faint. In order to get good statistics in a small patch of sky, we had to go faint. That's why I emphasized the magnitude earlier. So many of the thousands of planets found by Kepler are useful for statistics, but not useful for individual characterization of interesting planets. They're just too far away. So that's why you need things like K2 and TESS, which is an upcoming mission that'll get talked about as well by Natasha Battaglia tomorrow. We need those missions to find closer stars. So Kepler was for statistics, not for individual characterization. But we found this one. So it's a little big, but it's the right kind of star, it's the right temperature. The problem with Kepler 452 is it might not be there, which is a problem. The data we see are quite noisy, and the signal that we see when we see Kepler 452 looks extremely similar, almost indistinguishable from another signal we see due to a temperature change on the spacecraft. So we think, given we've done a whole bunch of characterization of this noise, we think this has about a 50% chance of being real, 50-50, toss of a coin. So it's either there, and we found something that could be Earth-like, or it's a false positive. So that's a bummer. But that is still currently the contender for the most Earth-like planet that we found. What else did we find? This is Kepler 186f. So you can see already, I'll just click back and forth, the color of the star is very different. Kepler 186f is orbiting an M dwarf. So we'll probably discuss this a lot today. What does it mean for an Earth-like planet to be orbiting an M dwarf? What does that mean for habitability? And I think that's still an open question. So Kepler-186 is rocky for sure. That's exciting. It's only about the size of Earth. It's the right distance from its M dwarf for the temperature to be right for in that range, 180 to 303 Kelvin. But it is orbiting an M dwarf, so we're not sure. It's Earth-like in its temperature and composition, but not in the profile of the flux from the star that it's receiving. So M dwarfs put out a much higher fraction of their flux as UV radiation, which is generally not good for life on Earth. But even that statement, like when life was forming on Earth, UV radiation was higher coming out of our sun as our sun was, getting onto the main sequence and everything. So it's interesting. When Kepler launched in 2009, people weren't really thinking about M dwarfs. The whole point of Kepler was to do stars like the sun. So the fact that the most interesting Earth-like planets we found are around M dwarfs really was a real right turn for everyone on the project to be like, wait, we have to really think about this carefully. So M dwarfs have really become the star du jour for exoplanets, which is exciting. And then since we're talking about M dwarfs, I'll show this. I won't show the animation because in the transfer to the windows it got really choppy. But this is TRAPPIST-1, which is a system of 7 rocky planets orbiting an M dwarf. 3 of the planets are probably the right temperature-ish for liquid water. So that's C, B, and E. C, B, or D, E, and F. D, E, and F. It's the 3rd and 4th and 5th ones out. And so I'll talk a little bit more about this, but we're finding many, many temperate rocky planets around M dwarfs. So it's becoming more and more important that we answer this question: are planets around M dwarfs habitable? And I'm hoping that I'll get a clear idea of the answer from some of you all today. Okay, so I'm talking a lot about rocky planets around M dwarfs. There are 7 we know of, and I won't go into detail. Meredith's going to talk about Proxima Centauri later. Angie's going to talk about habitable worlds later. But just to say, there are 7 that we found, rocky planets that are the right temperature around M dwarfs. So this is our sample right now this is our very anthropocentric, this is where we think life might be, on a rocky surface with the right temperature for liquid water, but they're all around M dwarfs. We actually have none around stars like the sun, which is the only place we know so far that life definitely exists, is on a rocky planet with liquid water around stars like the sun. So, is that going to stop us? No. So, we can extrapolate dangerously, and we have. So we didn't find a lot of things that look like the Earth. We have candidates in this size and temperature regime around stars like the sun. They just haven't been confirmed yet. So we can try to do statistics. So the question is, are Earths common? And we believe the answer is yes. So this is an earlier result from a few years ago now from a paper that Chris Burke and I and a bunch of Kepler people wrote. This is the posterior distribution of the probability of a FGK star having a planet in this range, 1 to 2 Earth radius. So you can see I've gone well beyond the 1.5 where we think it might be rocky. But in order to get any statistics, we need to make this bin big. We need to make it as big as possible. And then 50 to 200 days. So these are actually Venus analogs. How common are Venus analogs? Because that still gives us a handle on the problem. And what this is centered on, 33%. 33% of FGK stars have a Venus analog, according to this analysis. If you extrapolate even further out into Earths, and our error bars just got a lot bigger, this is the posterior distribution for really Earth-like things, rocky things, 365 days around sun-like stars. And this is a posterior distribution centered about 0.5, so 50%. But what I've done here is overlay a bunch of guesses, that's underselling their work, other people's work in the literature trying to do this. And you can see that we're spanning like orders of magnitude here in how common Earth-like planets are. And that's because we're extrapolating. And when you do that, you have to make assumptions about the form of your extrapolation and how big your bin is and that kind of stuff. So I wanted to update. This figure is also from Burke and Christiansen et al. I wanted to update for 2 very recent results that just came out in the last few months. So there was an upper limit by Danley Su and collaborators using the very, very latest set of Kepler data at 0.27, so 27%. They put an upper limit, a stringent upper limit. It must be less than that. And then Steve Bryson and a bunch of Kepler people put out a new analysis which is centered at 0.19, so 19%. Interestingly enough, the latest results out of Kepler diverge. So 2 teams tried to do an independent analysis, and one got a much smaller value than our original guess, and one got a larger value than our original guess, which I won't put on here because it's still in prep. The point of this to say is we have not converged on a value for how common planets like the Earth are. But, you know, if you want to take the sum, there was this comment yesterday about if you take a bunch of weak evidence and add it up, do you get strong evidence? You know, it looks like it's between 10% and 1, which for me is common. If more than 10% of FGK stars have Earth-like planets, that seems common because there's tens of millions of FGK stars throughout the galaxy. So that's
Jessie, are all of those on the right, the same period range and the same radius range?
In as much as possible. So one of these that I put on yesterday is slightly larger period range. I think maybe Steve's is slightly larger period range. So Russ and I might talk about this later. There was a group of people who came together and said, let's define the box and only tell me statistics in the box. So Danley did, but Steve didn't. I think I have that the right way around. Russ can correct me if I'm wrong. So what we tried to do was to say, please, for everybody doing statistics, here's the box. Can we all use the same box? And then Chris had done a careful job a few years ago of mapping everybody else's onto that box. So I did not, at the 10 p.m. last night, do a careful job of mapping Steve's on. So Steve's is a bit of a bigger period bin. Okay, the takeaway is we think Earths are common. We're still getting down to the, getting the error bars down. We have not ruled out that, it's less than 10%, but I would bet that it's more than 10%. Okay, so that's kind of the summary for how Kepler did with finding out how common Earth-like planets are. I want to talk about some of the types of planets we did find, just so this talk isn't entirely anthropocentric, where are the Earths? Because, my takeaway from yesterday was that we shouldn't just think about places that look like the Earth. So here are the other places. So hot Jupiters, I mentioned before, these are gas giants, Jupiter-sized planets that orbit their star in just a few days. These are actually some of the best studied exoplanets we have because they are so big and we're able to learn so much about them. So a lot of follow-up studies have concentrated on hot Jupiters just because they have a signal that for now is really approachable. So some of the things we've learned about hot Jupiters, they're typically single. There's only one planet in the system, and that gives you clues to formation, something to do with how the planet formed and migrated into a star, kicked out the rest of the planets in the system. Some of them are inflated over what we would expect for, an atmosphere of this composition at this temperature. So that's something we're still tracking down exactly why we think some of these hot Jupiters seem to be puffy. A lot of what we've concentrated on is basically, my husband makes fun of me, we're basically like weathermen in space. We're mapping out weather on these exoplanets, mapping out the cloud tops. So one of the things we can do is to make maps of the surface of the planet, very crude, one-dimensional maps of the surface of the planet as it's going around the star. But that starts to tell us about the atmosphere and hotspots, like where is it the hottest? Is it at the substellar point, or is the motion of the atmosphere moving it from the substellar point, which appears to be so? The exciting thing about transiting planets is when you take a planet with an atmosphere and put it in front of the star, and the starlight goes through the atmosphere, the spectrum of the planet's atmosphere actually gets imprinted on the starlight. So we can start to work out what atoms and molecules are in the atmospheres of these planets because of the difference in the stellar spectra when it's transiting and not transiting. So I have a list later, but we've managed to detect many atoms and molecules in the atmospheres of these planets. And then this animation, which I'll just show one more time, is showing one of the cool recent things we found about exoplanets, about these hot Jupiters, is they have these exospheres. So they're so close to their star that when the star does something, like in this case it's going to birth out coronal mass ejection, it actually is so close it just ionizes the planet and get this big wave of ionized hydrogen come off the planet, which we've been able to observe with things like Hubble. So that really tells us something about how planets can survive this close to the star, which is really interesting. Okay, so lava worlds. So these are the first unambiguously rocky planets that we found, are these rocks orbiting these stars so close, less than a day, that we think that the surface of the planet is actually liquid magma. We don't have as good a handle on these as we do on the hot Jupiters because it's so hard to find anything about them. They're so small compared to the Jupiters. We have a small number of density measurements where we have actually been able to measure the mass and the size so the size from transit method and the mass usually from radial velocity, sometimes from transit timing variations. So we have some handle. We know they're rocky, so that's exciting. We have an even smaller number of atmosphere measurements. It's hard to imagine sometimes how these could even have an atmosphere, and sometimes it's not really an atmosphere in the way that we think, but it's just the solar wind is actually just creating this like sphere of material around the planet. I just like this one, is fun. We recently found cyanide in the atmosphere of 55 Cancri E, which is one of these lava worlds, which is pretty cool. Oh, and I clearly didn't update that for the reference that I wanted to put there. Awesome. So those are lava worlds. Those are the two like really interesting classes we found so far. And now we're on to this mystery category, that big set of question marks I had before. Okay, so in our solar system, there's basically 3 different sizes of planets. You've got the gas giants, Jupiter, Saturn. You've got the ice giants, Uranus and Neptune. Then you've got to jump down to the rocky planets. There's Earth, and then you have Venus, Mars, and Mercury. So when we were building models of the solar system, how planets formed, before we knew of exoplanets, you were trying to create this, right? Like if your model didn't recreate something that had rocky planets close to the star and ice giants and gas giants further out, then you've done something wrong. We haven't actually found any solar systems like that yet, which is interesting. What we did find was thousands of these, super Earths, things in between the size of Earth and Neptune, and as I said, they have been a mystery. Is it just a rock that you scaled up? Is it a Neptune that you scaled down? So this has been a source of a lot of interesting observation and theory to try and work out what these are. So this is a result that came out of Kepler. This is BJ Fulton and Eric Pettigrew last year. This is the distribution of sizes of planets found by Kepler. So this is 1 Earth radius, and here's 4 Earth radius, which is Neptune. And this is basically the number of planets with orbital periods less than 100 days per star. And what you can see is it's bimodal. That's really interesting, right? There's structure here. So the first thing you can see is that small planets, planets smaller than Neptune, are much more common than bigger planets. So these are the Saturns and Jupiters out here. And so the dashed line is actually the raw numbers. And even in the raw numbers, there's many more smaller planets than bigger planets. And then the solid line is corrected for completeness, because it's harder to find those smaller planets. We miss more of them. So when you're correcting for how many there actually are, this difference becomes even more pronounced. There are many, many more small planets than large planets, which is really interesting. And you can see this bimodal distribution. So that kind of lends itself to the interpretation that perhaps this peak here are the mini Neptunes. These are the Neptune sort of things, volatile, rich atmospheres that are just a bit smaller. And that these are the super Earths here. So those are rocky things that are a bit bigger. And you can see this valley here is kind of where 1.5, 1.6, where we were expecting this transition to happen. Interestingly, one of the things we've discovered is the location of this valley between these peaks is actually insolation dependent. It depends on the star and how close you are to the star, which we believe relates to a mini Neptune's ability to hold on to its atmosphere depending on how far from the star it is. So closer to the star, this valley is smaller because it can't hold on to its atmosphere, so many more of them become super Earths and become mini Neptunes closer to the star. So this is really interesting, the structure down here. Again, because they're Kepler planets, we don't have a handle on the densities of these, so we're kind of guessing that they fall into these two categories, and we're working hard to try and get some masses for these things for which we have the radii. But yes, this is really interesting. Okay. I mentioned that transiting planets were able to measure the atoms and molecules in the atmosphere, and just because we're in this kind of audience, I wanted to point out some of the ones we found. 19 planets we have found water, like water vapor, not liquid water, but water vapor in the atmospheres of planets. 17 planets we found methane, so we're going to have a talk later about Titan, which I wrote down, that's Martin. So Martin will tell us all about methane, but we found methane in 17 planets. We found some other carbon-bearing species, so carbon dioxide and carbon monoxide in at least 13 planets. I wasn't sure about the overlap between those, so I just put 13 plus. But you can see the building blocks are out there. These planet atmospheres look like they have things that we have. The one thing I looked for that I didn't find, so there's phosphorus hydride, but I'm not sure if that will help us with the phosphorus question, which we heard yesterday was important for life. There's just like atomic phosphorus floating out there that we found. Okay, so these are there's lots of interesting stuff in the atmospheres of these planets. Okay, so those are the big classes of planets we found. I wanted to talk a little bit about the types of planetary systems we found. So because we have such a large sample, we can start to talk about how are they distributed. So we've been able to analyze the distribution and eccentricity, and what we can see is when you have a transiting planet, you don't get a lot. You get the length of the transit and the depth of the transit and maybe a little bit of information about the shape of the transit. But you can actually do a lot with that. The transit would be a different duration for the same period if the planet was eccentric, because it would be moving at a different velocity. A planet that's on a circular orbit is basically moving at the same speed the whole time. A planet on an eccentric orbit is speeding up and slowing down, which changes on average its transit duration. But we can see when we look at the distribution of transit durations in Kepler that they look basically circular. And this maps with earlier radial velocity measurements that planets that are closer into the star are more likely to be circularized, and planets that are far away are more likely to have a wider distribution in eccentricity. So that tracks. Most of the Kepler discoveries seem to be circular. We've looked at, in multi-planet systems, Kepler has many multi-planet systems. The one with the most planets is akin to our solar system. It has 8, which is Kepler 90. So we're able to look at basically the spacing and the sizes of the planets. It seems like, and I'm going to say this with a little bit of an inflection in my voice, it seems like planets in multi-planet systems seem to be fairly regularly spaced and fairly regularly sized, more so than the planets in our solar system. And I say that with a little bit of an inflection in my voice because there are recent results questioning that discovery and saying maybe it's just a selection effect, some kind of uncorrected for selection bias in the Kepler observation. So for now, I'm going to keep saying it, but with the caveat that maybe we have to see if that shakes out to be true. But it seems like the systems we're finding are not the same as the solar system. To bring it back to you guys here, it seems like our solar system might be different. We also found second binary planets, which was very cool. If anybody remembers Tatooine, we found Tatooine, which is very exciting. We have found disintegrating planetesimals orbiting white dwarfs. This is this really interesting systems that we found. We had seen polluted white dwarfs for a while, so white dwarfs with metals in their atmosphere that should have sunk down from the upper atmosphere and still seem to be there. And there was this theory that perhaps they were eating their planets, and that was polluting their upper atmospheres with metals. And we did in fact find a set of basically rocks disintegrating on like a 4-hour orbit around a white dwarf. And that seems like the exact sort of candidate for creating these polluted white dwarfs. So that's really cool. Another thing that is really interesting but less relevant for this crowd is that these systems that we found, a lot of them seem to be much more compact than our solar system. So many planets between where in our solar system we have the Sun and Mercury, where Mercury is our closest planet. We found many systems with many planets closer in than Mercury. So that's really interesting. And a subset of those are in resonance. So the same way the Galilean moons around Jupiter have this chain of resonances, we found planetary systems like that as well. So that is really interesting clues about formation, how these planetary systems form. I didn't just want to focus on Kepler and K2, so some of the other interesting things that we found, there seems to be a turnover in giant planet occurrence rates between 1 and 10 AU. So as you go out from the sun, you find more and more and more giant planets until somewhere between 1 and 10 AU, when you marry the radial velocity results with the direct imaging results, there's a turnover. It can't just keep going, otherwise with direct imaging we would have found many more planets than we have. And here's just, the problem is all of these different detection techniques haven't quite met in the middle yet, like we're getting really close. So these are some radial velocity results, and these are some direct imaging results. And basically you can see that the radial velocity results they just can't keep going the way they're going. There must be a turnover here. So that's really interesting. Super Earths, so this is this big mystery box of planets. They seem to be correlated with Jupiter-like planets. So gas giants on further out orbits seem to be correlated with super Earths. They seem to happen more often in systems where we see super Earths. And I'll get to why that might be interesting in a second. Free-floating planets, we're not going to talk about them basically at all, but it seems like the galaxy has many, many free-floating planets, rogue planets that have been either created outside of a solar system from a small gas cloud or created in a solar system and then flung out. There was a recent claim, which I put a little question mark next to because it was widely refuted, of extragalactic planets, so seeing planets in other galaxies via microlensing. And then I know we're having some talks about protoplanetary disks and formation later, so I'm not going to talk much about this, but The ALMA results, all these beautiful images of disks we're seeing, structure is ubiquitous. Things like rings and arcs and clumps are ubiquitous. So this is like lending credence to this idea that planets are common. Planets seem to be everywhere, and they seem to be everywhere from very early. Okay, the number of planets has been increasing exponentially for 25 years. This is a tweet for people who don't use Twitter, where I had looked at this plot of extrasolar planets with time, and I was like, is there a Moore's law for exoplanets? Moore's law is this famous, computing power doubles every 24 months, and I was like, is there a Moore's law? And Eric Mamajek wisely changed it to a log scale and drew a line and said, yeah. So it's doubling every 27 months. And his prediction was that we would hit 1 million planets by 2034 and 1 billion in 2057 if we kept going. So I dubbed this Mamajek's law. So just try and use it in everyday conversation. I'm trying to make it stick. So how can we keep this going? So this plot's a couple of years old now, but I'll take it on red that this trend has continued for the last 2 years. There are some really big missions coming up that will find even more planets, which is very exciting. So TESS, which is just started its second year of operations last week. WFIRST, coming up in a few years, we'll do a microlensing survey. And then there are a couple of ESA missions, which aren't on here, Gaia and Plato, which will also find planets. And if you take their yield predictions at face value, then we're on track. We're on track to keep doubling the number of exoplanets every 27 months, which, given that my job is working at the NASA Exoplanet Archive, is great job security for me. But also, importantly, TESS is supposed to find planets that we can follow up. So I've told you a lot about the Kepler planets and what we don't know about them. TESS is supposed to find planets that we find a lot more about. So that's going to be really awesome. So when James Webb launches, we're hoping that TESS will have found a fantastic sample of planets to do much more detailed atmospheric and density studies of. Okay, so I'm going to finish with the big open questions as far as I can tell for this crowd. Still an open question. We would like to have nailed this down, but how common are Earth-like planets? So that's the anthropocentric big open question. If we want to look for planets like the Earth, how common are they? Because this has really big implications, which we'll probably talk about in the panel later, for designing the missions that will find Earth. If Earths are very common, that changes the size of the telescope we need to build, for instance. Are temperate rocky planets orbiting M dwarfs habitable? They seem to be quite common. M dwarfs just seem to create scads and scads of rocky planets in the habitable zone. But are they actually habitable? That's a big question. Another one, is there a typical planetary system? And why doesn't it look like ours so far? And I put an asterisk here because the reason I think it's interesting to ask the question, is there a typical planetary system? Because I think, as far as I can tell, it's still an open question, is Jupiter important for Earth to have life? I've seen both arguments in the literature that Jupiter is bad for life on Earth and Jupiter is good for life on Earth in terms of like shepherding comets from the outer solar system and large impacts on the Earth. Or potentially, it's either directing them towards us or it's keeping them away from us. So one of those is good. So is there a typical planetary system? Do we need this result that Marta Bryan found a few years ago that Jupiters seem to be common in systems of super-Earths? Is that important? Is that relevant? Do we need to keep looking down that path? And then finally, are moons as common as they seem to be, extrapolating from our solar system? So we have been looking for exomoons in the Kepler data. There are several groups that have been trying very hard. There's one candidate that they haven't quite managed to confirm yet. In our solar system, moons are everywhere, right? Like almost all of the planets have moons of some kind. Are moons as common as they seem to be? And then the reason that's important is a similar, the other flip side of the point. Is the moon important for the habitability of Earth? The fact that we have tides that create tide pools, which are sometimes wet, sometimes dry, how important was that in the formation of life? And so if moons are common, that's great. If moons are rare, then maybe that has implications for life. So those are the big questions as I see them. I'm sure there are more. And I wanted to leave plenty of time for questions, so that's what I have. Thank you.
Questions for our speaker? Scott?
So I think this is related to our rocky planets orbiting M dwarfs habitable. I know there's been a lot of efforts in the radio to see if we can see magnetic fields for planets. Has there been any success in any way, in any wavelength about magnetic fields for planets?
That's a good question. I know I have heard of people trying. I'm not bringing any successes to mind right now.
No.
Can I comment?
Yeah.
So Not directly, but there are star-planet interactions between hot Jupiters and stars that have been observed where there's activity on the star that is linked to the orbit of the planet. So that suggests that there's a magnetic field on the hot Jupiter that's interacting with the star, but not for rocky.
Right. I think that'll be a hard one to make.
I think at one point you mentioned that there was a indication of a lot of Venus-like worlds, but it was hard to tell if that continued up to Earth-like worlds.
Right.
And I'd just like to point out that if it turns out there are lots of Venus-like planets and no or very few Earth-like planets, that's not necessarily a bad thing as far as habitable real estate in the galaxy, because it turns out with our more recent models of early Venus climate, that if you actually model it with a GCM, which has been done recently and hadn't been done before, that the behavior of the global cloud deck acts in an interesting way to stabilize the oceans. And the results we get now are that oceans on Venus may have lasted for 2 billion years or more, which might mean that on a Venus, the longevity of the habitable zone is within a factor of 2 or 3 of the longevity of the habitable zone on Earth. And if that bears out, then there could be a lot of life on a lot of Venus-like worlds out there.
It looked like there are a lot of Venus-like worlds out there, so that's good.
One of the things that you mentioned was that you didn't think it was maybe of interest to this crowd, and I think it is of a lot of interest to this crowd, and this is the degree to which solar systems are packed with planets. And you mentioned that ours is not so much.
Right.
And I think that this has potentially profound implications for the full inhabitants of planets that are within relatively close proximity of each other, should life be kindled on one of them. So in our solar system, of course, we're discussing whether or not we have bit swapping between Earth and Mars and all this, and whether or not materials could be transported even to the icy moons. There are reasonable chances for that. In the Martian case, it's much harder to argue that there would be transfer of already kindled life within the system. And so I think in terms of fully populating all the potential planetary niches, so to speak, within a given solar system, if life happens there, that it does matter a lot.
Right, that's a really good point. I have often thought about, so TRAPPIST-1 is a system which has 3 planets very close to each other that all seem to be habitable. I've often thought about the fact that, you know, in each other's skies, those planets are bigger than the moon. And if you were like a primitive civilization, if you were a civilization that didn't like have electricity yet, it would be possible to like observe life on another planet before you had actually like explored your own planet, because it would just be there, and that like you could see cities in the night sky. And I just always think that's amazing to think about, and what that might mean. But that's more of a philosophy.
Right. So I mean, there's the intelligence life aspect of it that you just touched on, but there's also, you know, microbial sized life-like entities being distributed through the system.
Yeah, so I think that would be much easier because these systems are, like, we say dynamically packed, meaning you could not put another planet in there and have it be stable. Yeah. So that's especially why these resonances are important, because you can get things quite close if they're in resonance, because the resonance actually keeps them stable. So you get these really interesting strings. So TRAPPIST-1, for instance, they're all in 3 to 2, 5 to 3, 8 to 5, this chain of resonances. And there's another system, KT-138, which is 5 planets all in 3 to 2 resonances in a chain, which is like 3 to 2 is pretty, spans close to like one, that means the period is only 1.5 times the next period. So
Is there, sorry.
Yeah.
Is there any way to tell whether those planets would then be also tidally locked as well as because that will make a big difference?
Yeah, so that's something I didn't really talk about with the habitability of these planets around M dwarfs. Some of them are so close that we expect them to be tidally locked, and what does that mean for habitability? You know, I think people stress too much about tidally locked and habitability, because, you know, if you do the thought experiment of if you were life that evolved on a tidally locked planet, like your day side's just a lovely, nice, warm temperature, it's perfect for you, or the night side, and then you find planets that are spinning around and the temperature is swinging by 50 degrees every 12 hours, wouldn't you just be like, how does life evolve there? Like, how do they cope with those temperature changes? I actually think that we might be strange. So yes, so some of these planets are tidally locked, especially the habitable zone ones around M dwarfs, and that is something that we need to make sure we have in our minds when we're, you know, developing this. But I actually think it's not a problem. I think people stress like, oh, but they're tidally locked. I'm like, I don't think that is, like, as long as the temperature's right, like, what is nighttime really for?
All right, we'll take one more question while our next speaker comes up and gets set up.
Yeah, Jessie, I was impressed by the list of gases that you have. Presumably those are from hot Jupiters?
Mostly from hot Jupiters, some from the warm Neptunes.
If that's the case, is it possible to use that data to see if these hot Jupiters are spinning prograde as they pass over the limb and you're only looking at the gas, the light coming through one side of it?
Ah.
Get a Doppler shift in the light.
So that would be, you would have to get enough signal to noise on the ingress of the planet compared to the egress to tell the difference. That, I think, would be challenging. We can see we can see when the orbits are prograde, but I don't think we have the signal to noise yet to see whether it's spinning, unless anybody wants to correct me. That's just, maybe with James Webb or the next generation of telescopes, but at the moment we're eking out, like if we add up all the signal to noise in transit, yes, there's order. So getting the ingress and egress, which is a small fraction of the transit duration, having enough signal to noise in each of those. I mean, if you had a really long transit, you could just chunk it in half and then see if there was a difference.
Okay, great. Let's thank our speaker. All right, our next speaker is Jim Casting, who will be discussing circumstellar habitable zones.
Okay, well, first, thank you to the organizers for inviting me to come down here. I've heard about Green Bank all my life, but I've never been down here. And I was one of the people who was highly influenced by Drake and Sagan and the first Green Bank meeting, and so it's a delight to actually see it with my own eyes. You notice that my title in the program is Habitable Zones. I added circumstellar here because I'm only going to talk about habitable zones around stars. There are people who define subsurface habitable zones on planets and moons within the solar system. I'll mention those in passing, but that's not what I'm going to focus on in this talk, and I'll come back to that a couple of times. Here's a rough outline for this. I'm going to start with the basic requirements for life. I can be really brief here because it's actually been, everything I'm going to say there has been, almost everything has been covered either by Lynn Rothschild yesterday or by Jessie just now. Then I'll talk a little bit about the definition and boundaries of the habitable zone, which is something I've worked on and off for many years. And then important recent developments, most of which were mentioned just now by Jessie. So I can do that quickly too. And then I'll finish up with a couple of slides on direct imaging, which we haven't heard about yet, but which to me is the most exciting thing that we're going to be trying to do in the next couple of decades. All right, I'm going to list 4 requirements for life. 3 of them are on this slide. Number 1, a planet with a liquid or a solid surface. This is what Jessie just said, why the Kepler team is interested in rocky planets. I think that's an absolute for life. Carl Sagan didn't think that, right? So if you have read Cosmos or looked at the movie that, he writes about floaters that might exist in Jupiter's atmosphere. There's some nice videos, which I'm not going to show here, but that is sort of analogous to fish with fish bladders that can adjust themselves in their heights in the water column. But these are highly evolved organisms, and I think you can't get to floaters in Jupiter's atmosphere. You can't get beyond the single. We all think, I think we all think that life goes through single-celled stage, and you just can't maintain a stable pressure temperature environment in a giant planet atmosphere. That's not controversial. Second one's you need a thermodynamic free energy gradient to drive metabolism and growth. Lynn said this in a different way. She said life is not a thing, it's a process. That process involves energy transfer. One definition of life, which isn't maybe the best one, it's something that uses a free energy gradient to decrease its own entropy at the expense of its environment. This is non-controversial also. Lynn talked about carbon. I agree with Lynn. I think life will be carbon-based. If you look at a compendium of all the chemical compounds known in the universe, something like 95% of them are organic compounds, and I don't think you can duplicate that with other elements. The fourth requirement is one that Lynn also talked about, water. There are people who want to look for life in liquid methane on Titan. That's fine. In our solar system, we can do that. In fact, we're going to go back to Titan with Dragonfly, and look at like Jonathan Lenine wants to send a boat there and go sample the methane lakes. So that's fine in our own solar system. I think water is probably a universal requirement. For extrasolar planets, it's particularly important because I would argue that we won't recognize, with extrasolar planets, we're not going to be able to sample them in situ unless we invent some kind of space warp drive that we don't have right now. So we're going to be looking at remote signatures from the atmospheres. We're not going to recognize it unless the life is water-based and on a planet within the habitable zone. Furthermore, that water and life have to be at the surface for us to see it, because subsurface life, like you might have on Europa or Enceladus or maybe even on Mars, is not recognizable at a large distance with moderate resolution spectroscopy. So that leads to first of all, the definition, the term that the astronomers like to use these days is eta sub Earth. It's the fraction of stars that have at least one rocky planet in their habitable zone. This term is very similar to the n sub e, the third term in the Drake equation, except that n sub e can be greater than 1, and this is normalized to 1. So that's because the Drake equation was invented to, try to quantify how many intelligent civilizations there could be in the galaxy. Eta sub Earth is to try to quantify how many stars you have to look at with a big telescope in order to find a planet that is like Earth. Other than that, it's very similar. The other thing that I'll say is we should be conservative when calculating eta sub Earth, because we are trying to develop these big direct imaging telescopes, which I'll talk about just at the end of my talk, and we don't want to undersize the telescope by overestimating the frequency of potentially habitable planets. All right, well, this leads into the second part, which is on the definition and boundaries of a habitable zone. I like to use the term habitable zone because it was used by Michael Hart. He didn't invent that term. The term, I think, was invented by Shushu Wang, who was at the 1961 Green Bank meeting. When I was in graduate school at University of Michigan, Hart published 2 papers, one in 78, one in 79, and he defined the habitable zone as the region around a star where a planet can maintain surface liquid water. I'll show you other people have thought about that. But Hart also defined what he called the continuously habitable zone, or CHZ, which is the region that remains habitable for some finite period of time. And all stars brighten during their lifetimes on the main sequence. Bright blue stars brighten faster than dim red stars, but that means that if the habitable zone at some time t0 goes from here to here, then at some later time t1, when the star has brightened, it goes from here to here. You can't point too accurately with this laser. The overlap between those two is the CHZ. So the CHZ is always defined for some finite length of time, which we usually take to be 4.6 billion years for our own solar system. All right, you can get in arguments about how to name the habitable zone. And so there's lots of different names for it. Harlow Shapley called it the liquid water belt in the 1953 book. That's what we're talking about, surface liquid water. Strughold called it the ecosphere. Lynn Margulis used to call it the Goldilocks Zone. Francois Forget more recently has called it the hunting zone, because that's the region where you might hunt for habitable planets. I think at a SETI meeting we should be leery of that, because if we find intelligent aliens, hopefully it's not the hunting zone for them. And then Elizabeth Tasker has a book and some papers recently where she says you should call it the temperate zone, because not all planets in the habitable zone are habitable, but not all planets in the habitable zone are temperate either. So we can argue about terminology. What we're talking about, though, is rocky planets with liquid water on their surfaces. All right, back to Michael Hart's calculations. As I said, he had 2 papers. The 78 paper was on the habitable zone around our own sun. The 79 one was trying to extend this model to different types of stars. In the first paper, he concluded that the 4.6 billion year CHC around the sun went from 0.95 AU to 1.01 AU. You get a runaway greenhouse in Hart's model at 0.95 AU, and in his model, if the Earth had formed 1% farther away from the sun, it would have frozen over and never recovered from that. And I remember reading that when I was a graduate student and thinking, oh no, I hope that's not really right, because then he took, in the second paper, he took the same model and applied it to other stars and found out that their continuously habitable zones were even narrower or in many cases non-existent. And so that was, I'm not sure I believed it at that time, but that was one of the things that motivated me to work on this problem, because I thought, I hope that wasn't really right. What are some of the problems with Hart's model? It was really a pretty simple model. The biggest problem, actually, in his model is that he had a bad greenhouse effect for calculation for CO2. He went out of his way, I think, to pick the weakest estimate of the CO2 greenhouse effect. And in his model, if you ever fully glaciated the Earth, you could never deglaciate it. Well, we know that's not right, or we think that's not right, because there's pretty good evidence that the Earth did freeze over 2 or 3 times in its history, so-called snowball Earth events, and it recovered quite nicely. That would have been a real disaster if that had happened during the Phanerozoic, but these happened during the Precambrian, and life sailed right on through for reasons that we still debate. The other thing about Hart's model is that there is a feedback involving atmospheric CO2, which is illustrated on this slide here, and I'll go through it in a moment. Hart actually had a CO2 feedback in his model, but it was based on what's called the Urey equilibrium, but wasn't really physically based, and it didn't operate very well. So as I said, we've worked on this problem on and off for a long time. From my way of thinking, the habitable zone is wide, and the main reason is because there is a feedback between atmospheric CO2 levels and climate. The atmospheric CO2 level is controlled by the carbon cycle, but it's mostly controlled by the inorganic carbon cycle, or carbonate silicate cycle, as opposed to the organic carbon cycle. And the inorganic carbon cycle is illustrated here. CO2 dissolves in rainwater and gives you carbonic acid. You use that to weather silicate rocks on the continents, releasing calcium and bicarbonate and dissolved silica, which go into the oceans, and then organisms use that, the calcium and the bicarbonate, to make calcium carbonate. They fall down into the deep ocean. Most of the calcium carbonate redissolves, but some of it coats the seafloor, and then the seafloor isn't just sitting there, it's being created at the mid-ocean ridges and spreading out, and you subduct these carbonate sediments. There's a process called carbonate metamorphism, whereby calcium and magnesium carbonates recombine with dissolved silica, with silica, which is by this time the mineral quartz, that reforms calcium and magnesium silicates and releases CO2. So this whole cycle recycles all of the CO2 in the combined atmosphere-ocean system on a time scale of about 500,000 years. If you freeze over the Earth, as we think happened during snowball Earth, then the weathering side of the cycle slows or stops, but volcanism continues, CO2 builds up, and if you have a better greenhouse model than Hart had, that will give you enough greenhouse effect to melt the ice. Most of the time in the Earth's history, we haven't had snowball Earth episodes, and we think that's because as the climate cools, then the silicate weathering slows and CO2 builds up. This also is, I think, most of the solution to what we call the faint young sun problem. The sun was 30% less bright when the Earth formed, but we weren't in a perpetual state of glaciation. It's probably because there was more CO2 in the atmosphere as a result of this cycle. There is some new work on this. One caveat that had been overlooked by me and by many people until fairly recently, and that's that if you have a planet that has either low volcanic outgassing rates or low stellar insolation, you can get limit cycling, where the planet repeatedly goes snowball and deglaciates. And that was actually Aichi Tajika who showed this a decade ago over in Japan, and I didn't pay enough attention to it until Kristen Manu wrote a paper 3 or 4 years ago pointing out that this might be a frequent occurrence on planets near the outer edge of the habitable zone. So I'll show you some habitable zones in a moment. Some of that real estate may be less favorable than other parts of it. Here is an old diagram of the habitable zone. We did a paper in 1993. This was not my figure. You can tell it was made by some Europeans because the distance scale has commas in it here. This is 1 AU and 0.1 AU. The vertical scale here is the mass of the star relative to the mass of the sun. It is an old slide. It had 9 planets in the solar system. Pluto's X'd out. The habitable zone from our 93 model is shown by this blue strip here. And of course, it's closer in for dim red stars and farther out for bright blue stars. This is the 0 age main sequence habitable zone because these habitable zones move as stars brighten. So if you want to do a diagram like this, you have to pick some time during the star's history. The outer edge, what we actually work on is the technical aspects of how you calculate that. The outer edge is controlled really by CO2 condensation. CO2 starts to condense and that changes the tropospheric lapse rate. We do 1D models and so we don't worry about things like condensation of CO2 to form ice caps. But people that do this now with 3D models, you can also condense the CO2 out to form ice caps. There's something that most people don't think about, but CO2 is also a really good Rayleigh scatterer. And so as you build up CO2 in a planet's atmosphere, it Rayleigh scatters a lot of the sunlight back to space, and so the planet's albedo goes up. So you get greenhouse effect from the CO2, but you also get an increase in albedo, and these compete against each other. So there's something we call the maximum greenhouse limit, which is as far out as you can get with the CO2 water atmosphere greenhouse effect. It's about 1.67 AU for a sun-like star. The inner edge, Hart was basically right there. In fact, we still like his number, 0.95 AU. You can get a runaway greenhouse there where the oceans evaporate entirely. There's a variant on that called the moist greenhouse where the ocean is still liquid, but the stratosphere becomes wet and you photodissociate the water and lose hydrogen to space. Our old limit was at from the 93 paper was at 0.95 AU, right where Hart had it. More recently, we've revised the calculation because Colin Goldblatt showed that if you use new absorption coefficients for water vapor from the high temp database, you get much more absorption in the visible, and that changed the limit. I'm not going to dwell on the details here, but I had a postdoc, Ravi Kaparapu, who along with my grad student Ramses Ramirez redid all the habitable zone calculations, and the habitable zone moved outward then because of the increased water absorption. It's shown here on this slide. I'll show you one that's easier to see. This habitable zone is now shown in terms of the effective solar flux instead of distance. And the reason this expands the habitable zone so you can see it more clearly around different types of stars. As I said, I'll show you a better one, but Earth ended up right on the inner edge of the habitable zone in our 1D model, which was not good because we don't think that the Earth is really on the verge of a runaway greenhouse. Fortunately, people have been doing climate calculations now, runaway greenhouse calculations, with 3D atmospheric models, and this is where Francois Forget's group over at University of Paris has been doing, I think, the best job. They showed with a 3D model that had the high temp coefficients that if you take into account the general circulation of the atmosphere, you get rising air in the tropics and descending air at 20 or 30 degrees latitude, and that dries out the air, and so you get less water vapor, and you can radiate away energy through that. In fact, Pierre Humbert had shown that 20 years ago in a paper about the Earth's tropics. Ray called those radiator fins. So anyway, if what LeConte et al. Did is they showed that if you take that 3D effect into account, then the habitable zone, the inner edge, moves right back to 0.95 AU, where Hart had it and where we had it for a long time. There are also people who don't believe theoreticians, and so they don't believe any of these calculations because it's hard to do things like clouds. We neglect clouds, or we actually paint them on the surface in our model. But you can define empirical habitable zones limits. David just mentioned that Venus might have had liquid water during the early part of its history, but we're pretty sure it hasn't had liquid water for at least 500 million to 1 billion years. The last time it was resurfaced, there's no fluvial features there. Mars looks like it did have liquid water early in its history, even though it was beyond the edge of the habitable zone. So actually, that may be because it had molecular hydrogen in its atmosphere, which can extend the outer edge. Anyway, if you put that back into the model, this is a fairly recent habitable zone diagram. Now, again, with stellar flux here relative to the Earth on the x-axis, and in this case, stellar effective temperature on the vertical axis. Here's Venus, Earth, and Mars. This yellow curve here is the runaway greenhouse limit. The blue curve is the maximum greenhouse limit. Early Mars is just outside that. This red curve here, that's the recent Venus limit. So we define a conservative habitable zone. This is what we get from the climate models. That's this region out here, and then an optimistic habitable zone, which is if you don't believe the inner edge calculations. Notice that this is populated with a bunch of Kepler objects, which we just heard about. This is I'll show you a better version of this. So some of these Kepler objects are bigger than 1.6 Earth radii, so they're not likely rocky planets. Okay, recent developments. These have been talked about. You just heard about Kepler. Kepler has been a revelation in our knowledge of planets in general, but especially of rocky planets. Value of Eta sub Earth, Jessie mentioned that it's still being debated. There's a paper that was in press a month and a half ago with Chris Stark as the first author. There's some good estimates for Eta sub Earth for M stars. It looks like it's about 0.2. I think this Dressing and Charbonneau estimate is still accepted. For FGK stars, the Sun is a G2 star. Eta sub Earth, according to Stark et al., is 0.24 plus 0.46 minus 0.16. So, as Jessie said, it's very uncertain, but it's unlikely to be less than a tenth. Okay, so I'm almost out of time. What have we learned from Kepler? Well, there's a density peak at 1.6 Earth radii, so as Jessie already said, planets bigger than 1.6 Earth radii are probably not rocky. There's a planet, potentially habitable planet going around Proxima Centauri, which I think we'll hear about later in the conference. There's this TRAPPIST-1 system, which was mentioned in the last talk. Here's our most recent habitable zone figure. Sonny Harmon, my former student, draws these things. But here's the TRAPPIST system down here. 3 of those planets are in the conservative habitable zone. One's here. Here's Proxima Centauri b down here. So there still are a number of Kepler objects in there. And then the last 2 slides here, I just want to briefly mention direct imaging. It's what we can do so far to characterize telescopes is only look at transiting planets. And the chances of seeing a transit, especially for a planet going around a sun-like star, really small. It's 1 in 200 for Earth around the sun. So you have to look at 200 G-dwarfs before, even if everyone has an Earth, you have to look at 200 of them, which means there shouldn't be any close ones. So what we want to do with direct imaging is look for reflected light from the planets so you can see the planets around nearby stars. There are 2 missions that NASA has been studying hard, LUVOIR and HabEx, that would be big space-based direct imaging telescopes, and that's how I think we're eventually going to find evidence for life. So I'll leave you there. I'm out of time. I'll leave you with these conclusions, and thank you for listening.
Questions for our speaker?
So for the carbonate silicate cycle, which seemed to be really important for expanding the habitable zone, it seems like that requires plate tectonics. Can you say anything about what the possibility, or not the possibility, but how common plate tectonics might be amongst rocky exoplanets?
Well, it's a good question. It's a big debate, amongst astronomers and geoscientists. It may or may not require plate tectonics because there are ways of recycling CO2 without plate tectonics. For instance, on a stagnant lid planet, if you have a carbonate platform there and then a point volcano that goes through that, you can volatilize a lot of CO2. That's exactly what's happening in Sicily. Mount Etna pokes through that's a hotspot volcano, poking through a carbonate platform, puts out as much as 1/6 of the total volcanic CO2 going into the Earth's atmosphere today. So that, you may or may not need plate tectonics, but plate tectonics almost certainly makes that cycle run more smoothly, and so it's very important.
Jim, so it's wonderful to use the Earth and ask would it have liquid surface water because it makes the habitable zone a nice, well-defined problem. But like with Scott's question, if you get rid of the plate tectonics, it'll change the calculation. So what other varieties of exoplanets would change the calculation? And should we maybe even have a more optimistic habitable zone if we allow planets to be a little larger, a little smaller, different compositions, and so on?
So, the CO2 greenhouse effect is actually pretty independent of planetary size. That doesn't depend on plate tectonics. That's a radiative transfer calculation. But if you allow other greenhouse gases, you can change things. Sarah Seeger has published papers saying we know that molecular hydrogen, surprisingly enough, can be a good greenhouse gas. And if you allow yourself a lot of molecular hydrogen, you can move that habitable zone out to Venus or Saturn's orbit, 10 AU. But that's where I go back to saying we should be conservative when we're defining the habitable zone if we're using that to design these space telescopes. Once we got the telescope built, we're not just going to look in the habitable zone, we're going to look all around there. We'll hopefully see all the planets out to some outer working angle. And so then we can check out theories like Sarah's idea that you could have habitable planets at 10 AU.
All right, we'll take one more question while our next speaker gets set up.
Jim, you seem to suggest that going from one-dimensional to three-dimensional models gives something like a 5% change based on this additive cell argument. But also clouds are a big part of all of this, and maybe cosmic rays, and maybe the ozone cycle. What do you think the real uncertainty is in these one-dimensional calculations, and is it now required to make a three-dimensional GCM model?
Well, Francois Forget's 3D model gives almost the same, they moved the inner edge back to where we used to have it, and their outer edge is about where ours is, so they're fairly consistent. Now, whether or not he's doing clouds correctly on the inner edge is debatable. That's why I showed you an empirical limit. I would argue with you, David, that I don't think that Venus had liquid water early on. It's a long argument, so we should have it over lunch. But I think you have to rely on empiricism from our own solar system at some point. I think Venus is too close.
I mean, just a quick response. Have you seen the work that the Goddard group did, where they include the GCM
Michael Way?
Mike Way? Because what they find is that it is the behavior of the clouds that really changes things. That if you have a slow rotator and you model it with a full up, basically they took the GISS Earth GCM and modified it for Venus, and the behavior of the clouds does something really interesting where it basically becomes permanently clouded on the sunward side and permanently clear on the anti-sunward side, and that ends up, it's sort of an ideal case for keeping things cool, and they find that stabilizes the ocean for a significant period of time.
See, then you have to lose the ocean late in the planet's history after the crust has solidified. It's hard to get, where did the oxygen go? Whereas if you lose the water very early, then there's a magma ocean and the oxygen gets sucked up by the magma ocean. So that's what I think.
Yeah, well, let's talk about it over lunch.
Let's thank our speaker again. Our next speaker is going to be Kelly Smith from Clemson University, who's going to be discussing the concepts of life.
And now for something completely different. I think it's amazing that I've been invited to this place with all this history. It's really neat to be walking around and seeing all these pictures and everything of all the work that's been done here. I was in the bathroom this morning and I was thinking, this toilet looks like it dates back to the 1950s. and then I thought, I wonder how many famous behinds I am sharing. This is what philosophers do when they have time on their hands. So I'm primarily a philosopher. My function is a philosopher. I'm trained as an evolutionary biologist too. For short periods of time, I can pretend to be an evolutionary biologist, and you'll probably see some evidence of that in the talk that's coming up. So talking about life, we were sort of divvying up the work in this panel, and I was given the life thing. I thought, it's much more fun to talk about ethical stuff. Life stuff is tricky. In my experience, when you're presenting life stuff, either people in the audience think that the question of what life is stupid and weird, or they think that your answer to the question is stupid and weird. So it may very well be that everybody in this room doesn't like the talk, but for independent kinds of reasons, right? And one of the things I'm going to try to do here is I'm going to try to think about this question from a philosophical point of view, maintaining a nice high altitude so I don't get bogged down in a lot of the weeds of the argument. I personally think that is part of the reason why we don't really have a shared conception of life, is because people allow themselves to get bogged down in the details in ways that are counterproductive. And I'm also not going to provide a definition. What I'm going to do is I'm going to talk about this a little bit. I'm going to make some comments about why I think we haven't gotten a consensus, and then I'm going to sort of suggest a way that we might reorient the way we think about the problem to get something more like a consensus, and you'll see why I qualify that in a second. And if people think this is interesting, even if they hate it, then I will call that a success. So, Okay, so whether you like it or not, science is in some sense metaphysics, right? I know that scientists don't like to hear that, but it's true, right? If you're doing biology is the study of life, you have to have some account of what life is. Now, to the extent that we're talking about an ultimate question of life, you can't avoid questions about what's real and what's not, which is metaphysics, right? It is the case, though, that for bench science, you don't need to deal with the ultimate question of life. And I think this is part of why a lot of bench scientists don't like this question, because you can do perfectly good science with more of a working definition, and you don't need to really worry about whether your definition matches anyone else's definition. As long as your definition allows you to answer interesting research questions, that's all that really matters, right? And the biological species concept is an interesting example of this. It's a concept of species that clearly doesn't apply to most species that exist, but people have used it for a long time, and it's been useful in lots of different kinds of ways, right? On the other hand, it is crucial in some sense that the categories that biology uses are real. Otherwise, it's hard to see how biology is actually a science. So, what does that mean in practical terms? Well, if you're a bench scientist, it's fine to say things like, look, I don't have time to think about ultimate questions about life. That's fine. It's fine to say, here's my definition. I'm just going to call it a working definition, and you're just going to have to deal with it. That's fine. Right? What is not fine is to say that trying to define life is either not worthwhile or it's not scientific. That's not okay. Or saying that you don't need an explicit definition of life even at a working level, right? And that last one's important because, as several people have pointed out, a lot of the areas of biology now are being forced to use some notion of life. Even if you want to talk about things like shadow biospheres, a biosphere is a living sort of realm. And so you have to have some implicit notion of life. And if that remains implicit, what that means is it escapes critical scrutiny. And so you end up with a notion of life that's never very well articulated and has all kinds of problems that you don't even realize, right? And let's make this quote here from Friedrich Engels, the co-author of the Communist Manifesto. He said, to refuse to do philosophy is to be a slave of the worst philosophy. So when scientists go, I don't like this philosophy stuff, I'm like, well, look, you've got philosophical positions, you just choose not to think about them, so they're probably going to be kind of crappy, intuitive philosophical positions. But, it's not like you're actually avoiding philosophy, you just are avoiding talking about philosophy. Okay, so we're going to have to talk about natural kinds a little bit. I'm sure that some of you have heard a little bit about this. I know that, even philosophers don't really like to talk about this too terribly much. If you go all the way back to Plato, when he was talking about science, he said the natural kind is what happens when you carve nature at the joints. So rather than sawing through the femur, you go to the joint and you carve that bird up in the way it's supposed to be carved up. And the scientific categories we have to be isomorphic to things, and I'm not going to get into that word too much. They have to be isomorphic to things that really exist in the outside world. If they're not, we have problems. So an electron is an electron regardless of what we think about it. A natural kind is something that is the way it is regardless of whether or not it matches human interests. If we are doing something different than that, if we're just sort of coming up with definitions that meet human interests at the moment, and we don't care whether or not they're isomorphic to reality, then science becomes something more like storytelling. And you guys might not find that to be a problem, but there are philosophers who will actually adhere to that view that science is just a form of storytelling that we particularly like, and you don't want to go there. Just trust me, you really don't want to go there. Okay, so conceptual baggage. The problem with natural kinds is not in the concept of natural kinds per se, it's in the way that concept has traditionally been cashed out. So Aristotle started all this stuff really after Plato. He sort of fixed it a bit. Aristotle and the ancient Greeks had a weird conception of reality, right? They had this idea that reality behind the world of appearances was perfect and immutable, right? And so you knew you had gotten hold of a natural kind when you found something that was static and unchanging behind the variation that you see in your experience. And the classic model of this is when they discovered that music, which seems to be just, completely arbitrary, is actually based on these mathematical ratios, and they got really excited about this. The Pythagoreans formed a cult, and all kinds of weird things happened at that point. So that's why Aristotle says that to define a natural kind, you have to specify necessary and sufficient conditions for the genus and the species, and the criteria by which you know you've got it right is you have a clean category with no gray cases, nice clean borders, because that's the way reality works, right? Then later on, classical physics and chemistry came along, and these are by and large structurally based sciences, so they're dealing with structures like atoms, and that model worked pretty well for them too. There's only one periodic table of the elements, and there's not a lot of gray area between elements, though I've talked to some chemists who say, it's a little bit more complicated than that, but whatever, right? By and large, one periodic table of the elements, nice clean categories, nice clean boxes around them, right? And so this bias that started with Aristotle for different reasons, I think gets imported to classical philosophy of science, where philosophers sit around and talk about what science is, this notion that you have to have necessary and sufficient conditions and clean boundaries, right? That really wasn't questioned until about 30, 35 years ago when philosophy of biology became a thing. When I was coming out of grad school, philosophy of biology was really starting out. And people started really thinking about biology. And one of the things that we found irritating at the very beginning is we were constantly being told that biology wasn't really a science because it doesn't have laws. Well, maybe the problem is not with biology, maybe the problem is with your theory about what science is. So certainly requiring clean categories is not going to work in biology. It's just not going to work. And there are lots of reasons for this. Evolution is how you get life, at least for a first approximation. Evolution is how you get life. Evolutionary entities are based on their functions, not their structures. They're based in evolution, natural selection selects phenotypes, not genotypes or other kinds of structures. And then evolved categories are in constant flux. Maybe this is what Lens meant the other day when she talked about life being a process, but process ontology is weird, so I don't know if I want to endorse that or not. And of course, similar things can be said about the requirement that there are laws in biology. And if you take this kind of stuff seriously, you have a choice to make. Either biology is not really a science, or the traditional model of philosophy of science is somehow fundamentally mistaken. Right, and you have a choice to make. You could decide that biology is somehow lacking and we have to wait until a better biology comes along. I personally think that's absurd, that what we probably have is a situation where the classical models of philosophy of science are all based on physics, and that's just one kind of science. Okay, so I think biology is real. It's not, as Cleveland has claimed, like alchemy. It's a terrible analogy for all kinds of reasons that I won't get into right now. But the bottom line, for the purposes of this talk, when I'm not talking to a bunch of philosophers, is just to point out to you guys that there are philosophical accounts of natural kinds that are not like this, right? That's all that really needs to be established, is there are respectable models of natural kinds that allow for blurred boundaries of the type that biology produces. Boyd, for example, has a lot of work on this, as do several other people. And roughly speaking, epistemic question you run into then, if you take that kind of account, is not so much how clean the boundary is, but how much agreement there is amongst the people who really know the field, right? That's the indicator that you've gotten things right, not the cleanliness of the boundaries, right? So one way of putting it is that a strange attractor is no less real for being really difficult to describe. It still may represent something real in the world, even though it's fundamentally statistical and fundamentally vague, right? And if you want sort of a fun, although testable in principle way of applying this, if you're talking about life concepts, one way of thinking about whether or not you got it right is, if we were to consult with a board of alien biologists, would they roughly agree on what life is? Would their conception of life overlap to a large degree with our conception of life? If yes, then we probably have it right. If no, one of us is mistaken. And we'd have to work out who's mistaken and why they're mistaken, et cetera, et cetera. Okay, so one of the common moves that people like to make is towards some sort of pessimism about definitional stuff, and I've written on this, so if you really want to know the skinny on why you shouldn't let your friends be pessimists, you should read some of my work, but here's a quick sort of view. People might say, oh, well, if the question is how much agreement there is, and there's really no agreement, then we've got three sort of related moves we might make. One, let's just not define life. We can't do that right now. We'll wait until biology is fully mature and a definition will plunk into our laps and then we'll all be happy, right? Operationalism, well, life I'm going to define as whatever it is that I like to measure, right? And I will just say that if there are redox reactions or whatever, that is life, and then everything's good, right? Or relativism, life is whatever anybody I like says it is. Anybody I respect as a scientist, if he says that's life, fine. And then someone else can say something that's very different, and that's fine too, right? I've thought about this for a while, I think that scientists like these more than they should for reasons they shouldn't endorse, right? First of all, I think sometimes they don't grasp or don't care about the deeper ontological implications of some of this kind of stuff, which is forgivable. They're not philosophers, right? They think, I think sometimes that the only respectable way to talk about natural kinds and things like that is the traditional one. They don't realize that there are actually other ways of thinking about this that are perfectly respectable. And finally, and probably most importantly, it gives them a technique to avoid getting bogged down in stupid philosophical argument, right? Which again, I sympathize with, but it's not really a good argument. Okay, so when they talk about the traditional accounts from a very, very high level, I realize there's an enormous number of variability here, and I'm going to simplify a whole lot. There's three basic ways to think about life that people have talked about. There's the thermodynamic way, which tends to be how the physicists think about it. Something like systems that are far from equilibrium, where entropy can decrease over time, right? The nice thing about these kinds of accounts is that they're highly general. I mean, they come from physics, so of course they're highly general accounts. And there's a lot of value in having an account that's highly general. Certainly having a negentropic system is going to be a necessary requirement for life. I can't see how you could possibly have life without that. The problem with them is that they're highly general. They're so general that they're going to include things that pretty clearly are not life, right? So for example, storms are not alive. They have some interesting attributes that might make them life adjacent, but they're not alive. And so if your account can't differentiate between a storm and a cell, I think that's a major problem. So it's relevant, but it's not quite right. Metabolic accounts, it's a little hard to get clear statements of exactly what a metabolic account is, but it's something like chemical systems capable of converting energy and maintaining homeostasis. It's something like that. There's variations on that theme. The good thing, again, is that homeostasis and the individuality it makes possible are certainly going to be necessary for life. You're not going to be able to have life without something like that. The bad part, there's a couple of weird things about this. First of all, whenever anybody uses the word chemical in life definitions, I always wonder what in the world that word means, right? So it's not entirely clear what work that word is doing, because if all you mean is composed of matter, then it's universally applicable and it's not helpful. If you mean something more than that, I need to know what you're talking about. So that's and it's clearly the case that metabolic accounts tend to be tied to chemistry, I think largely because they come out of the origins of life community, which is largely a biochemistry community, so it's a disciplinary thing more than anything else. It's also not entirely clear that it doesn't include what I call cheap homeostasis. So, what exactly is homeostasis? A star has a balance between the forces of fusion in its core and gravity. That's homeostatic in a sense, but it's not the kind of homeostasis that's indicative of life, right? Okay, and then there's the evolutionary accounts. Here's the NASA definition: a self-sustaining chemical system capable of Darwinian evolution. The words in parentheses really should be taken out and thrown away, but that's the way the thing is normally stated. It's good because life is almost certainly going to come about through evolution, right? Unless you're talking about design, which is just evolution second order, right? It's been put in place by something that evolved, right? And so it captures these unique evolutionary aspects of living systems. And this is, for a long time, this is the account that I espouse because it's close to being right. There's something very close to being right about this. There's also something deeply weird about it, right? The really bad thing about this is that it doesn't apply to individuals. People sometimes talk about it doesn't apply to sterile individuals. No, it doesn't apply to individuals at all, because individuals don't evolve, populations do. So if you really want an evolutionary account, you have to talk about life being a property of populations, not individuals, which at least for me is getting a little too weird. It's not impossible in principle to do that, but it's very strange. And so again, it's like the biological species concept. Even though it's clearly wrong, there's something about it that makes people want to pursue it. And for a long time, I was stuck in that loop. So here's a thought experiment, right? You can't have a philosophy talk without a thought experiment. Imagine we send a probe to Europa, and imagine this probe is designed in such a way that we can't interact with anything we find there, we can just observe. So it goes down through the ice cap, it's swimming around the oceans, and over a long period of time, we observe just a huge profusion of diversity. There are all these organisms swimming around, and they're interacting in complex ways, and it looks like they have sex and reproduction and life and death and producers and consumers and predators and prey and the whole 9 yards, right? It's just a weird ecosystem, right? We can't take them apart to figure out what they're made of. All we can do is observe them. I think that most people would very quickly conclude that that is absolutely a living system, right? And questions like, well, what's their biochemistry like, are interesting and important questions, but they're not central to deciding whether or not those things are alive. It's kind of hard to imagine that you would take one of them apart and go, well, given this biochemistry, I thought it was alive, but I was wrong. That's just very strange. So it seems to me that this is the core intuitive concept of what life is. Or to make it a little bit more clear, the core concept of life has to do with how a system functions, and in particular, its display of adaptive behavior. That's what makes something alive or not alive, right? Function is really all evolution ultimately sees, so any account that's based on evolution is good. It should be based on functions, and life is really not about structures, except to the extent that a structure is actually necessary for that kind of adaptive behavior, right? So part of the problem with definitions of life is that every discipline has looked for structural components that its discipline likes to talk about and made that part of the definition of life, when in many senses that is missing the point. Evolution is full of multiply realized things, convergence like Lynn was talking about before. That's very common in evolution because evolution doesn't care about structures. So here's a core concept of life. I'm not going to call it a definition, call it a core concept. A system capable of a high degree of adaptive behavior by whatever means that's achieved, right? And by adaptive here, what I mean is behavior that is performed for the sake of the organism. There's a lot of literature on this in philosophy of biology I won't get into, but that's what we mean by adaptive behavior. Not a behavior that happens to be there or happens to benefit the organism, but a behavior that has evolved because it benefits the organism. It's also clearly necessary, and it might be a sufficient criteria for life. It's a bit vague, right? So like the boundaries are unclear when you say significant. It's a little unclear exactly what you're talking about. And it does definitely apply to individuals. The bad things about it, at least what some people will think about, I don't think they're actually bad things, but some people will think these are bad. It's a little unclear how much significant it is, but biology produces fuzzy categories, so no kidding there's going to be some slop in any definition you put forward. How can you measure this easily? I grant you, it's going to be hard to design something to put on a spaceship to measure this very well, but I'm a philosopher. I don't care about that. I'm interested in trying to figure out what life is. You guys worry about how to measure it. That's your problem. And it's a real problem. It's just a different problem, right? And life is not a perfect term, by which I mean it doesn't come in black or white, like pregnant, right? So if you adopt this conception of life, you're going to have a smear where you're going to have, well, that's a little bit alive, or that's life adjacent. That's an excellent example of a life, and everything in between, right? And for some people, that makes them uncomfortable. But again, biology is like that. Okay, so if we can all agree that that's a core concept, then we can use it as something like a genus concept of what life is like. It may not be the whole answer to what life is like. There's a paper by Mishler and Brandon from '87 where they talk about species concept, which has the same problem, right? And what they basically say is, look, on the one hand, there's no single definition of life that captures everything you want. On the other hand, you can't just go, whatever, right? So maybe we can compromise. Maybe we can say, look, what is non-negotiable about a species? And they say, monophyly. If a group's not monophyletic, it ain't a species, right? So we'll put that forward as like a core concept, and that's non-negotiable. And then if you want to take a monophyletic group and divide it up in 7 different ways, you know, an ecologist wants to divide it this way, a physiologist, that's fine, right? And so I'm suggesting maybe we do the same thing with life. We can say, look, the basic idea of life is this capacity for adaptive behavior, right? And then if you want to take that category and subdivide it in other ways based on whatever your interests are, that's fine. At least then we can say that we're all talking about basically the same thing, that the real category we're talking about can be defined, right? Okay. I'm suggesting basically that we already have agreement on this, at least at the intuitive level. We've just talked ourselves out of it because of our disciplinary commitments and our focus on the details, right? Life is not a mechanism, it's a product of mechanisms. So any discussion of mechanisms involved in life is missing the point unless those are actually necessary. So if it's really true you can't get life without organic chemistry, then organic chemistry might be part of the definition of life. I'm personally not convinced of that, but maybe that's the case. Okay, I will shut up now.
So I wonder what's your take on some information theoretic concepts of life, and whether we can consider, for instance, algorithms that are adaptive, that display an agantropy as livings like cellular automata or some maybe even AI algorithms. So.
Well, let me give you a sort of guarded answer. The guarded answer is, in principle, yes. I don't think that the kinds of models we have right now, the cellular automata and things like that, they're anywhere near rich enough to do that. But certainly, people have asked me about artificial intelligence. So, like, if you had a robot that can pass the Turing test, I would argue not only is it intelligent or rational, but it's alive. And people don't like that because they intuitively think of life has to be squishy and chemical, but that's a dumb qualification for life. If the robot behaves in the kinds of ways that living things behave, it's alive. It's just alive in a different way than other kinds of things. Well, okay. So in principle, yes.
Hi, 2 sorts of comments. First, you hit on the question of life being statistical. I took philosophy of biology about 38 years ago, so I'm right on with what you were commenting about it. It's always we're cousin to philosophy of physics. And the statistical part's right, but in addition, the other thing that's very different is that it's historical. So you get a molecule of water, you don't care if it's been in a hydrothermal vent or hanging out in Europa, it's going to be fine in your glass of water. You get an organism showing up, a student in your office, it's all about where it's come from before and its evolutionary history and its life history. So those make it critically different. But I was thinking very much about your thought experiment, and I think this is why I don't like it. When I talked to the science advisor for Star Trek, that's exactly the sort of approach they used, and that's fine if you're in the living room. But to me, that's an analogy to ALH 84.001, that as soon as you come up with something like that, people would run back to their labs and say, is there some chemical abiotic mechanism that would show those same features that we've missed? So is there an abiotic way to recreate these sorts of interactions and so on that we just simply hadn't known about before people would be willing to accept that as a life form?
And abiotic here means that it's not the kind of thing that biologists on Earth study right now?
No, that it would be some sort of chemical mechanism. Maybe you have to have high pressure and, XYZ chemicals, and then you mimic exactly that.
Aren't you begging the question, Lynn? So you call it abiotic because you've decided that it's not living and it just mimics life. But if it's sufficiently complex in its adaptive behavior, my argument would be it's alive.
Yeah,
you're just unwilling to grant it that status because it's not what you're familiar with.
And that's why I made the point yesterday about the Da Vinci and the water, because I believe somewhere out there's either something that is a natural kind of life, in which case we don't have the definition to be able to do it with these multiple approaches, or it's a matter of taste and it's not a natural kind, and then you're free for defining it any way you want.
Well, yeah, except what you're talking about when you talk about natural kinds is clean boundaries, necessary, sufficient conditions. And so, like, if you make Cleland's kind of move where you go, let's wait until some magic structural component comes along and it all becomes clear, that sounds neo-vitalist to me. I think that's a really bad move. But maybe we just fundamentally disagree on this, right? So.
All right, one last question from the back.
Let me follow up on Lynn's point. What if, so let's take the Martian meteorite, for example. It's kind of similar to your thought experiment. We saw something that looked like life. So that, you know, maybe it wasn't. Also, that face on Mars, you know, the picture that looked like life, but wasn't. So where do you draw the line between when you drill down through Europa's surface and you see things that look like life, but where do you draw the line between, you know, whether it's life or not?
Well, okay, let me address the second question first, then I'll come back to it. So where do you draw the line? That's a bit ambiguous, and it's going to have to be. Any definition that does justice to how biology forms categories is going to be fuzzy. And if you just insist on having clean boundaries, then we're just going to have to go separate ways, because I'm going to say that's the way you get stuck in an endless loop and you'll never get out of it, unless this secret thing comes along that fixes all your problems for you. ALH is a horrible example. ALH is, there's no behavior of any kind in ALH. It's just sort of ancient evidence that might be interpreted, like that is, I would argue there is not very good evidence of life in ALH. You could argue that it might best be interpreted as having been associated with life, but it's certainly not the kind of thing you would point to and go, well, that's clearly a lie. It's at best a very marginal case.
All right, let's take our speaker.
Yeah.
Before we get started with the next speaker, I'd just like everyone to turn around and say hello, Jill Charter, who's now tuning in. We're glad we have you there on the other side. All right. All right, so our last speaker before the coffee break is going to be Jen Macalady, who will discuss life in the solar system.
Thank you very much for the conference organizers, and I'm very happy to be here. So the talk that I was going to give here was somewhat similar to what Lynn said earlier, and so I'm just going to thank Lynn for warming up the crowd, and that's going to allow me to drill in a little deeper, so we're going to be just fine. I am a geochemist and a microbiologist at Penn State, and I'll take a little moment to introduce myself since I haven't met most of you before. My group works on energy and how that relates to the distribution of cells in the environment. So this is the general focus of my lab. And in particular, we're interested in energy extremophiles, which I would argue are the only relevant kind of extremophiles. And the reason I say that is that if you're living in pH 0 solution, for example, but you have tons of ATP, these protons that are leaking into your cell are not a problem. You just pump them out. But if you don't have enough ATP to do that, you're suddenly cooked. So energy extremophiles are organisms that are able to survive at really low energy flux rates, and that's sort of one of the main things that we're interested in. And I'll just give you a couple of examples of places that we go to try to look for those kinds of organisms so that we can inquire how they do what they do. So this is a sinkhole in the Bahamas. Those three dots that you see up there are divers. It's about 100 meters deep, and there's this little window at the top, and then there's this huge cavern beneath. And the life that's in the sinkhole is mainly on the walls, and it's on the walls in biofilms because if you're planktonic in that environment, energy flux is low enough that you get eaten faster than you can reproduce. So you have to prevent yourself from being eaten, and that means you have to live on the walls where things can't get you. And so even though along the walls there's hardly any light, so these are actually phototrophic biofilms that are on the walls of the sinkhole. They're not where they're supposed to be. They're not below the window where there's more light. They're on the walls because they can't grow fast enough to outcompete predators. And so it's this lasagna-like biofilm that we were just shocked the pants off us, actually. We couldn't believe it when it was found by divers exploring this cave. So you may be familiar with work in the Black Sea. There are very low light adaptive phototrophs there. Magical Blue Hole is our field site in the Bahamas. There's this pinnacle matte biofilm at 30 meters. And when we measure the amount of light that's reaching the surface layers of that biofilm, it's as extreme or more extreme than the Black Sea isolate, which is BS1. So what it comes down to is that each bacteria chlorophyll molecule in the cell is absorbing, on average, a photon about every 8 hours. And that's really, really slow. If you take that kind of a measurement and you ask, what is the maintenance energy that organism is able to sustain, these numbers are not going to mean anything to you, but I just wanted to put them up there to show you that we can actually make these calculations and that there's a quantitative sort of limit that we can describe for cells. So it's 1.625 times 10 to the minus 15 kilojoules per cell per day. So that's, in the paper, that was described as the lowest maintenance energy ever measured, but the truth is that we haven't measured very many. So we've measured 3 or 4. So we're still looking for what the diversity of maintenance energy requirements might be. We also recently started work underneath glaciers in glaciated places, including Svalbard, circled in red here. So if you want to find places where there's not very much energy flux, you go to a dark place, you go to a place where there's not very much organic carbon, and you go to a place where there's not very much chemical energy. So liquid water is great for delivering chemical energy to cells, and so this is a frozen place. There's not very much chemical energy reaching these cells because of water movement. There's certainly no light, and so we go there to look for other kinds of organisms that might have low maintenance energy. Hello? Got him. Okay, this is not published yet, but the spoiler is that when you look in the stream sediments, the sediments that the water is quickly carrying through these subglacial systems, you get organisms that look like soil from the surface. And if you look instead at the frozen till that's been underneath the glacier for thousands of years, you get organisms that you don't expect, organisms that we've never met. And so they may have unique mechanisms for surviving in these conditions of low energy flux. Last but not least, this is me and my group 3 days ago. This is a cave that's 500 kilometers, half a kilometer underground in Italy. And we're here because we are looking for a third kind of very low energy flux system. These are pretty scary looking biofilms. They're about half a meter long sometimes. And they're in a place where we expected to find nothing really. This water is anoxic and sulfidic, and it has no methane. And if you write this sort of thermodynamic menu of reactions that could support life of any kind, you get the answer that there's not very much energy available. And of course, it's permanently dark. And so the real question is not the snapshot, but how much energy flux can you get? And this is hard for humans because we go to a place like this where we're really not supposed to be anyway, and we measure the chemistry and we go, oh, there's not very much delta G available. And but the reality is that these cells, they have thousands of years. And so as long as their energy flux is great enough to combat the forces of entropic doom that are pulling their cells apart, then they're fine. And in fact, these biofilms that are very conspicuous, I mean, the divers that discovered these were scared to death. They were like, what is it? And so these are slowly growing, but really diverse, like as diverse as soil. And they're turning over really, really slowly. So their sort of reproductive rates and their cell division rates are on this time scale of thousands of years. So these are low energy flux systems. We don't really know how they work. They're hard to study because they're going so slowly. But we know that they're out there and that they're sort of conspicuous. They make these biofilms that are, piles of slime that you can see from a long way away. These are just pictures because they're so beautiful. Okay, I'm really excited about this system because we think that one of the metabolisms that might be in use is the so-called Berzelius reaction, which is the sulfide-controlled reaction to form pyrite. This is the reaction beloved of Echtershauser, and it's written up there for you. And here's a review paper about it. I won't say much more about this because we don't have anything published yet, but we think that organisms could conserve energy this way without too much problem, that we just haven't looked in the right places to find them. Okay. Now, this is the part of the talk that I was supposed to give, and so I will try to reiterate what Lynn said earlier and also fill in some gaps that I think are interesting, perhaps not from the convergence point of view, but just from the point of view that if we want to understand what Earth life is like, we should be holding up a mirror in as many different angles as we can. So all my students are familiar with this slide. They always have this as a test question eventually. So if you encounter a sentient alien familiar with the usual rules of chemistry and physics, but they've never been to Earth, they ask you what Earth life is like, what do you say? What do you say? Well, you say, for one thing, all the things that Lynn said. It's carbon-based, it requires other common elements for structural and catalytic functions, requires liquid water as a solvent, it harvests energy from light or electron transfer reactions at disequilibrium in the environment. So all of those things you've heard multiple times already. And I just put this up there to show you, because I love thinking about energy transduction. These are the kinds of electrical potentials that life can harvest. And this is not magic. This is all the kinds of reactions that take place with liquid water as a solvent, because this is the stability field for liquid water. So this is nothing, there's nothing mysterious about this. And all of the catalytic molecules that life makes are also in this electrical potential region. And likewise, Lynn talked about the photosynthetically active part of the electromagnetic spectrum. It's no surprise that we don't have any organisms that like to harvest UV. That would be suicidal for a carbon-based life form. We do have some uncertainties about this end of the spectrum. We have organisms that we think can use, 700 to 800. Those are interesting, but they're particularly intriguing because that means that you could have an ecosystem based on geothermal light rather than starlight. And that's sort of interesting if you have a planet or a moon that has an inhospitable surface but a geologically active interior. Okay. Other things, sensitive to UV and shorter wavelength photons, evolves in response to conditions outside cells. That's the process part that we keep talking about. And last but not least, extant Earth. This may not be life's first rodeo on Earth, but we don't have any way of asking about that. So we can talk about extant Earth life sharing a common ancestor, the same genetic code, common energy currency involving high energy phosphate bonds. And I'll just put this slide up here. Lynn showed this very same tree, this Boseian tree that's very simple and nice. And there you are in the animal twig. And the fact that these three domain lines converge means that there was a common ancestor. And this is not artistic license. This is based on statistical analysis of nucleic acid sequences. Sometimes people forget that. Okay, here's the genetic code. There it is, pretty picture of the genetic code. And here's the energy currency. And let me just take a second to say that I think it's really is going to be brilliant to use synthetic biology to find out whether or not other options are equally sort of probable. And that's one of the things that Lynn talked about. This is not what I do, but I think it's a great approach. Okay, so things that Lynn did not necessarily talk about are in this list. And I'm going to just go through these. Can somebody tell me how much time's left?
You have about 10 minutes.
Okay, 15 minutes. All right. The first thing about Earth life that seems rather obvious, but it's kind of struck me one day not very long ago. It's really old. And by that I mean not just with respect to the formation of the Earth. So here's the formation of the Earth and the formation of the Moon. You know, this time was violent enough that we don't have rocks left around to look at. And so that may have presented some challenges. But there's evidence that life really quickly picked up the pieces and got going. And so that is something that makes me think that this is a process that evolved from chemistry and physics on the environment of the Earth, and that it's not necessarily rare. But not only is it old with respect to the age of the Earth, it's old with respect to the age of the universe. I mean, you can imagine a universe in which life is easily begun and easily extinguished. And you can imagine this universe where through time life is, blinking in and out in various locations. Well, that's not really the picture. I mean, if life is, about this old, that's a significant fraction of the age of the universe. And that has implications for our search for life elsewhere, as well as our understanding of what our planet is doing. Okay, it's old. It's mainly too small to see. And this is not a mystery either. Life is too small to see mainly because diffusion in water is slow. Water is the solvent that brings energy to cells, and things diffuse through water slowly. If you have a small cell, you can have a higher metabolic rate and reproduce yourself faster. So this is not a mystery at all. Life should be very small, and it is. So life you can see with your eyes is there. Here's a different view of the tree that's much more modern. This is Laura Hug. A few years ago put this tree together, and the picture is the same. This is eukaryotes over here, this insignificant looking twig. And most of these are also microscopic, but this whole tree is smaller than you can see. And you can see things that are about 70 microns in diameter with your eye. All right, well, how small should life be? It should be as small as it can be because of this metabolic rate problem, and still allowing the machinery that you need to have cellular functions. And so the National Academy in 1999 put this report out that said free living organisms require a minimum of 250 to 450 proteins, along with genes, so genes take up space, and ribosomes, which are protein factors, those take up space, necessary for their synthesis. So a sphere capable of holding that minimal molecular complement would be 250 to 300 nanometers in diameter, including the membrane. So this panel decided that cells could be as small as 250 plus or minus 50 microns in diameter. And it turns out that that was not too far off. I want to point your attention to this purple part of the bacterial domain of this 3-domain tree. This is called the candidate phylloradiation, and most of those cells, if not all of them, are smaller than 200 nanometers in diameter. So they're all, and I'll come back to this later, they are all either symbiotic or parasitic. It's not really clear yet, but they're very small cells that live in close association with other cells. So this is a significant fraction of the diversity on Earth that we just met a few years ago. Okay, I want to just, this is a side. Here's a human hair for scale, and there's this myth that eukaryotes are big and prokaryotes are small. Things with a nucleus are big. It's not true. Lots of protists are tiny, and lots of microbial cells and other domains are big. And so here's the size range of free-living protists. They get very tiny. Here's a large bacterium and some small protists. So just trash that file. Okay, very old, too small to see. It's really diverse, and one of the things that my group thinks about is what is it about the environment that has led to this ever-increasing diversity trend that we see in all taxa. Okay, we're doing a great job of discovering new diversity. Here's 1987, here's 1997, this is just the bacterial domain, and here's 2016. We're doing great, going gangbusters. But what does it mean? So here's another subset of that tree I showed you earlier. Everything with a red dot we haven't been able to grow in the lab yet, so we don't know much about it. There are some theoretical estimates for the global microbiome. Here is one recent one that showed up in PNAS in 2016, Losi and Lennon. And they used some statistical theoretical arguments to conclude that the global species diversity is somewhere in the trillions, the low trillions. That was quite a scandal, I can tell you, but there have not been any other real attempts to estimate the global diversity. But note to self, this is more than the number of stars in the galaxy. More recently, and to many of our relief, there is another estimate that is more based on current census results, but still kind of theoretical. Loca et al. Have proposed that there are only a couple of million species on Earth. I think this is lowball. I think the truth is somewhere in between. And
OTUs?
OTUs, yes, I'm sorry. That is total jargon. That means operational taxonomic unit. Just substitute species and you're fine. Okay, so jury's out on this, but this is like how many exoplanets are we could do this kind of curve for microbial species that people have been thinking about for exoplanets. I haven't done that, but it's a great idea. One more thing I want to point out about this beautiful tree is that it's kind of collapsing into a two-domain scenario. So like birds or dinosaurs, eukaryotes or archaea. We can talk about that later. Okay, I'm going to go fast now. But one of the main things that we haven't talked about yet is that life is really symbiotic on Earth. We haven't fully realized that because the most of the life is tiny and we can't see what it's doing in the environment, and we keep trying to grow it alone in the lab and it doesn't work great, but we're still not quite getting the message. Information and energy trading between cells is rampant. It's the standard, it's the norm. Life on Earth is constantly trading. And so these are just, I mean, I can talk for hours about this. It's not just microbes, and it's between every different kind of level of taxa. Okay, I'm gonna skip that. Can't do this talk without mentioning Len Margulis, who was the first to show convincingly that we're just walking ambulatory microbe houses. Okay, more, this is how we think chloroplasts have proliferated in plants and algae. You can see that not only were there primary symbioses, but secondary and tertiary symbioses, and we've actually caught some of these in the act. Like you can go to the modern ocean and see plastids being captured by algae. All right, I'm going to end here with a quote that got me into science. So in high school, I read Lewis Thomas' The Lives of the Cell. And what he said was, my mitochondria comprise a very large proportion of me. I suppose there is almost as much of them in sheer dry bulk as there is the rest of me. We can now measure those kinds of things. Looked at in this way, I could be taken for a very large motile colony of respiring bacteria operating a complex system of nuclei, microtubules, and neurons for the pleasure and sustenance of their families, and running at the moment a typewriter. So that was prescient, and it's just gone that way. We just, more and more, the more we learn about life on Earth, the more we learn how much it is interacting on every kind of level. Okay, so this is other stuff that I don't have time to talk about, but if you're interested in biological energy quanta or the basal power requirement, I love talking about those kinds of things, and you can catch me later. And I'll stop there. Questions for our speaker?
So, do we stand to learn something from any environment which has non-zero free energy, but where we don't find life, or is there no example of that?
So far, no good. I mean, I keep trying to go to places where there shouldn't be much going on, but we do. We find life everywhere that we can measure.
So there is no place that has free energy that doesn't have life.
If you put it on the menu, they will come.
The surface of the sun is not free.
That's true, but it has to be habitable.
We haven't measured for life there yet.
All right, they're in the back.
Your biofilm is isolated from the cave. Is that disconnected from the surface, like the system that Unstott and Lisa Pratt looked at in the gold mines in South Africa?
Right, so it's an analogous situation, but the key here is the time scale. So nothing is isolated on a sufficiently long time scale. And so it's about the rates. It's about how much energy is going to reach there in how much time.
The other question, sorry, but it relates to the earlier question about not finding life anywhere on Earth. And has life been shown to really exist, multiply and grow in Don Juan Pond?
I have no idea what that is.
Don Juan Pond is a lake in Antarctica, and it's a calcium lake.
Mm-hmm.
And although organisms seem to blow into the lake, nobody to date, at least that I can think of, has been able to show that there is any active metabolism of the organisms that blow into the lake.
Sounds like an interesting place. I don't know the answer.
It is an interesting place.
Yeah. Very interesting.
Question from me?
Yeah, I want to go back to the very beginning of your talk of the low energy environments and photosynthesis, and you found these organisms in mats rather than free living, and you attributed that to predation. But I'm wondering whether it's because of organic carbon. I had a technician years ago who said that every photosynthetic organism was a suspect mixotroph to prove otherwise, and I suspect she was right.
Yeah.
That they're not really living on one photon, every fortnight.
Right.
That they're supplementing it with acetate from dead cells around or from the extracellular matrix or whatever.
Right, great idea.
Have you tested any?
Yeah, so the organisms that are the primary producers they don't have any of the genes that you would expect for heterotrophy.
Doesn't matter. Give them some acetate and see if they take it.
Well, they will eat acetate.
Yeah, there you go.
Yeah, but I think that heterotrophy could be part of the answer, but I also know that there is intense predation of organisms that are
But what I'm just saying is they may not be living on that low photon, they may be taking up acetate and so on from their environment, and that's how they're really functional isotrophs.
Mm-hmm. Yeah, I mean, at that point, you would take anything you could get. Okay.
In your talk, you talked about the entropic doom and the power requirement to keep it from doom.
Right.
Now, presumably there are environments that have less and less and less entropic doom, more and more stable. And if that's the case, there should be no lower limit to this energy flux requirement of life. Is that right, wrong? What do you think?
Right, so you can make models of this. If you get less and less entropic doom, for example, at low temperature, right? So if you're at low temperature, you don't have as much thermal destruction of molecules, but you also then have this problem of liquid water being able to bring you the energy that you need. So it's not going to be a simple equation.
You could freeze for a couple of million years.
Yeah, I mean, these are things that have implications for the extension of human life. I mean, lots of, I'm sure that there are people who've made models for cryogenics, for example, for human tissues.
So if there's some bacteria that would like to be frozen for a million years and then come back and then for a day and then go back.
Well, I haven't been able to ask them whether they like it. I mean, we freeze them all the time.
And then they come back to life, no problem.
No problem.
All right, it is time for our coffee break. So let's thank our speaker again. So here is kind of the plan. Kelly mentioned how we kind of divvied up territory and stuff like that, and how he would have preferred to do ethics. And I wish he told me that last night, because I would have been like, Kelly, you're on.
You would have been live?
Yeah, really. So I'm an anthropologist. So my job is to kind of provide an overview of some of the relevant terrain for ethics and such things, but I'm doing it anthropology style. So I'm not doing it in the way that a philosopher would. I am doing it in a much more kind of applied way. And what I'm doing here is kind of lobbing out some ideas, some stuff for you to know about, some things to think about, and I'm trusting that my colleagues, including Ted, including Michael, including Jim,
and also that Cassie will speak from the perspective of planetary protection, that others will explore a lot more of this both in their talks and in their panels. So I'm just trying to kind of open up a bit of space. So first then I'll talk about some relevant Earthshots and Moonshots. I'll define trouble somewhat briefly. Then I've got a couple of acknowledgements to make. And I'll talk about some themes in searches for life and obviously changes in the context of the searches, because although we're in the same place where it all started, the entire world has changed around us, right? And then I'm going to give you a number of examples of the kind of trouble that humans get into with other life. I'm going to note why it could actually be worse for extraterrestrial life, assuming that we can extend our sphere of interaction. Well, first of all, assuming it's there, but second, assuming we can interact with it through our technology or whatever. And then in closing, I'm going to have a suggestion and also a big question for you. So that's the plan. So our brief here, as you know, was to think about progress or to discuss progress and challenges in astrobiology that we expect, but also think about future plans that might require several decades' work and possibly technical or intellectual advances. I'm not going to be talking about technical, I'm going to be talking about intellectual though, because we have a lot of groundwork to do in my opinion. First of all, I second Steve Dick's comments from yesterday regarding one set of Earthshots continuing to integrate humanities, social sciences, and philosophy into astrobiology, not as a peripheral activity, but as an essential one. And then second, Moonshot, I love the idea of forming a center for the study of cosmos and culture, which would, as he said, catalyze and lead not only studies of the astrobiological humanities, but also the relationship of humans to the cosmos, past, present, and future. And I'd also like to highly recommend that you read Steve's books, both his recent one, sole authored, and his recent edited volume. They are excellent, very valuable groundwork. I'd also just like to mention the paper that we just wrote for the Astro 2020 Decadal Review, and I can happily send you the link. We sent it out for endorsement less than 30 hours before the deadline. That was my bad. Some of you, and there's laughter of recognition in the audience, some of you would receive the note. I just want to tell you that within 24 hours we had 119 signatories. So there's something there that the community agrees needs doing. I'm not going to speak any more about that because Steve covered that, although it is an area that I'm very, very interested in. I'm just going to add something else, though, that intellectual advances for astrobiology should also include some sound ethical groundwork for us and for future generations, and the creation of a culture in the scientific community which can sustain that continued groundwork. It doesn't just happen. Both of those are really challenging things to do. Blumberg himself noted at a symposium on the discovery of extraterrestrial life, the Royal Society in 2011, that missions take a long time to plan, fund, receive, and interpret data, can extend through the entire length of a career and beyond. These missions are often generational in character, and a scientist may have to depend on his, her, or someone else's children and grandchildren to reap the full harvest of a project that they initiated. And he was, as usual, absolutely right. But I want to flag to you that the full harvest of those astrobiological projects, that it's going to be complex, it's going to be mixed, it is not going to be all good. And so I think personally that we owe it to those future generations. And I think we're all aware their lives are going to be challenging enough, right? If you teach, or if you've got children or grandchildren, or great-grandchildren, whatever you have, pets, anybody, future generations, they've got plenty on their plate already. So I think that we need to be thinking ahead as members of a culture of collaboration, collaborating effectively by setting them up as well as possible in ways that will last after we ourselves are gone. So basically kind of in the spirit of, the way that Barry is continuing to animate these proceedings himself, I would hope that what we do in these rooms may actually help somebody foster something meaningful in years ahead. So just a word about trouble. The phylogeny, taxonomy, taphonomy, and afterlives of trouble. That's something I wish I could take the time to define and diagram for you, but maybe in the Drake Lounge later on. Give me a napkin and a magic marker and we'll go. But for the moment, I'm just going to say trouble is kind of like life.
I know when I see it, Kelly has a much better set of definitions, but I'm just going to go with that one. There are lots of different types and magnitudes of trouble, obviously. Some deserves a lot of attention, others, meh, who cares? But telling the difference is not always simple. Non-trivial trouble tends to persist. You can't usually eliminate it. Sometimes you should be anticipating it, mitigating it, reducing it if that's at all possible. There's a lot of trouble that can't be fixed. It should be acknowledged. And our task here is to stay with the trouble. So, a little bit more on what all of this means. Some of you may have recognized I am borrowing from the magnificent philosopher Donna Haraway, who wrote this brilliant book called Staying with the Trouble, Making Kin in the Cthulhu Scene. And this is her answer to the Anthropocene. It's like, no, it's something else. It's something primordial, tentacular. It's really quite different, her approach. And she says, trouble, this is how she opens this brilliant book, trouble is an interesting word. It derives from a 13th century French verb meaning to stir up, to make cloudy, to disturb. And we live in disturbing times, mixed up times, troubling and turbid times. And our task is to become capable with each other in all of our bumptious kinds of response. And she notes that mixed up times are overflowing with pain and joy, vastly unjust patterns of pain and joy. And here I want to just mention, I thought, Martine, your mention there of the intersections of stupidity and grace. I thought that was another brilliant distillation of the same problem. Exactly. So here we are. I am in this talk going to be focusing more on the stupidity, and I'm going to be focusing more on the pain. I wish that I had more space to talk about the joys of all the magnificent forms of life here on Earth, but they are, broadly speaking, in trouble, and so I don't get to do that. So, but anyway, her task that Haraway defines is to make kin in lines of inventive connection. So to make relationships is a practice of learning to live and die well together with each other in a thick present. Anthropologists talk about thickness as well. We don't like to distill things and make them simple. We like to keep them complicated. So she says our task is to make the trouble, to stir up potent responses to devastating events, settle troubled waters, rebuild quiet places. But stay with the trouble, which is kind of a hard thing to do, actually, in a discipline such as astrobiology. We are so focused on the deep history of life, trying to retrace the very beginnings, the origins, and we're also so focused on projecting into the future. It's hard to be here. It's hard to be right here, right now. But she says, staying with the trouble requires learning to be truly present, not as a vanishing pivot point between awful or Edenic pasts, or apocalyptic or salvific futures, but as mortal critters. And she also specifies we're entwined in finished configurations of places, times, matters, and meanings. So here we are, and this is kind of one of my jumping off points, one of my inspirations, and we'll go forward from there. You don't want to summarize Donna Haraway, you just want to let her speak for herself. Okay, so acknowledgements and gratitude, these are the happy acknowledgements. Barry Blumberg, I was very fortunate to meet him just once. But a shared taxi ride on the way to the Royal Society really meant something to me. I just want to reflect, for those that knew him well, who had that privilege, I know a lot, kind of remark on his quality of presence, the way he was just really, really there with you in the room. And he, as Carl mentioned, he didn't want to talk about himself. It was always, he just wanted to hear about you. He wanted to learn. So it was, anyway, it was a really inspiring few minutes that I got to have. I want to thank our sponsor. I want to thank the Scientific Organizing Committee, the local organizing committee, and our Green Bank hosts. I love Green Bank so much. I haven't been here enough over the last 15 years, but I've been here a few times, and it's been amazing every time. So thank you for those who are welcoming us back. I want to thank you for engaging in the conversation. I want to thank those who are watching who may be related to me. And I also want to thank the many humans and other than humans who inspire me and teach me continually. I think it's just important to practice gratitude. Before we launch into the more difficult stuff, first of all, I want to acknowledge that West Virginia exists on the traditional territory of several American Indian nations, including the Shawnee, Cherokee, Tulo, and Saponi. You may recognize some of those names as nations which you think of as being further west. There's a reason for that. They were forcibly moved. So it is important to acknowledge that this is where we are and that this happened, less than 200 years ago. Obviously, there are representatives of these nations around today, but this landscape has been completely transformed. Also, it's hard to believe when you're driving through the Monongahela National Forest, completely clear cut. So that is a reconstructed forest, that is second growth as a result of a decision made around 1910 is my understanding, which was the result of phenomenal erosion and all of those things that happen when you cut all of your trees down. And there were also some staggering local extinctions, species that you would never believe could be hunted to the very brink of extinction. White-tailed deer. Yeah, there's lots now, that's because they were reintroduced. Otters, et cetera, and so it goes. So the local history of actually where we are encapsulates something that I want to be talking about today. There are some species that may not make it in the long run. Some particularly endearing bats in particular, but there we go. But meanwhile, so this forest, as I say, it's not primordial, it's completely managed, it's completely humanized, it is there at our discretion, and it is also, of course, used for profit, most of which goes to the central US Treasury rather than to the local area. Anyway, I want to just flag that then these displacements, losses, reshapings, and the silences, these are processes of contact. And since contact is what's kind of dancing in the background here, right, that is part of what has animated SETI in particular, I think it's really important to know. And finally, we are in the midst of catastrophic anthropogenic global biodiversity collapse. This isn't just my opinion, you've read the news. So there is that, as well as the loss of traditional cultures and languages, and all of these things dance together. And for me, when I am here in this place, this is as much of kind of my mental furniture. These are the spirits that kind of hover around and animate my thinking, as much as the ghosts of observatory directors and telescope builders and astronomers of the past. So they all kind of come together into this discourse for me. So I'd just like to ask you to stay with me, stay with the trouble. There is some difficult stuff ahead. I am being actually very careful not to show many images, and I will explain as I go why that is, but there are some which may stick with you. I want to say it's easy to come down on a side here as well. Everybody has their own positions. We all have our own ethics about what we do and what we don't do and what we wish other people would do and what we think is right. My intent here, I'm not here to debate that. It's to describe, to do some anthropology, describe what humans actually do with other life and to keep those realities in view. So there's, of course, the whole realm of what we should do. And I've got other colleagues here who are better qualified to delineate those things. But I just want to flag that I think it can really help us to recognize some patterns in human interaction with other than human life. To think about the kinds of trouble that are already here, might continue, and might develop. Okay, so as for why search for life is important, it's so frequently said in SETI and in astrobiology that it'll tell us who we really are. It will finally let us know our place in the universe. That's a very common line. I've always found that perplexing. I suppose it makes sense in terms of taxonomic diagrams, but it's not usually meant that way. It's usually meant from a philosophical perspective or even a religious perspective. So I guess I want to ask, what if who we are is not an answer to be discovered out there? What if it's a decision that we make here? What if the way that we live that question, are we alone, is actually more important than any discovery we might ever make? And what if we start addressing the ways in which we make ourselves alone here on Earth? The reason for the biodiversity collapse is we're killing life all around us, all the time. And sometimes it's accidental, sometimes it's intentional, sometimes it's for fun. And all of the other ways as well in which we set ourselves aside from other life, making ourselves special, but thereby making ourselves alone. So almost everything has changed around the search. I've got kind of two slides on this one. First of all, what a magnificent time and place and group with whom to reflect, because so much of the history is here. As you know, the search for life elsewhere has changed so much in its results and its practices since the start. Tremendous advancements in technology. I mean, the pace is breathtaking. So much has been done. although there's so much yet to do. So the current results, as I understand them, no obvious technological life loudly transmitting from the closest known planets. So thanks, Breakthrough, for confirming all that for us. Still so much more work to do, obviously. We've got the moving threshold of detection for living planet atmospheres, characteristics on exoplanets, so that is going to be coming. We've got upcoming life detection missions in the solar system. Things are moving. But searches happen within this global system, right, of science, technology, politics, economics. And if we think about where we are compared to various landmark dates, say 61, 69, 76, so Ozma, Apollo, and Viking 1, wow, the whole world has changed. And that changes the meaning of what we're doing here. So geopolitics, our knowledge of biology, human and civil rights, my goodness, some very significant changes since 1961. Animal welfare, it's an idea now. It really wasn't so much, or not to the same extent that it was, in these early days. Our understanding of human evolution, completely transformed. I wish I had a whole other talk to tell you about that. Human mobilities, we are so much more global and in so many ways. Multivocality in the human we are realizing that we is composed of so many, and that representing all of those different voices matters. That's a fairly new realization on the global stage. Of course, we've got biotech, synthetic biology, the internet, AI, all of these different things. Knowledge of animal behavior and minds, completely transformed since, say, 1961. The rise of experimental ethics and limits on our curiosity. That was still, these were still some fairly new ideas in the early part of the latter century. Humans to space, of course, total cultural refiguring of Mars in particular, the rise of the virtual, and again, we've got all these different collapses of diversity, and we have climate change. So everything has changed around this core idea, and what I want to submit to you is that it has to change the way that we think about astrobiology. So, I had that already. But also the cultural distance between Earth and other worlds is collapsing. As I often tell my students in various classes, culture and visual representation do not obey the laws of physics. So for us, obviously, Earth and Mars, literally very far apart, not easy to get between them. But culturally speaking, Mars has been steadily annexed. We are more and more there all the time. And that has some really interesting implications. So our effective distance, though, is also starting to collapse. There are so many different plans for different kinds of faster transit, and some of them will come to pass. So we are at the beginning of something there. We are now in a situation where machines really can be our avatars in space. It's still pretty basic. It's fantastic rovers, but that idea of human action at a distance mediated by machines, it has begun. And again, we can expect that to continue. And the other thing, of course, is that the long-term promotion of searches for life has continued to build public curiosity and interest. So that's a thing in itself. Thank you. Okay, so here are just a few different themes. First, I always say, well, weird life, you want to find some of that. Look in the mirror. Nothing personal. Humans, oh my God. It's the joys of being an anthropologist. It's just like this endless kind of catalog of human weirdnesses. I just want to flag for a community where people are very focused on logic and deduction. Typically, I just want to flag most human endeavors, logic does not prevail. You know this in life, but some of that intrudes into science as well, as you know. Stories and narratives matter. Visual representation matters enormously. I'll tell you an example about that later on. Silences and absences matter. So when you notice them, it's a good idea to mention them. Sex and reproduction matter. I just mentioned that. I mean, it's an obvious truth, but because one of the things that happens a lot, kind of in general space speculation, is just sort of like magically babies get born on Mars. If you actually think about how that would kind of shake out in practice and the ethics and the risk involved, both to the women and to the children, there's a lot there to talk about. And similarly, when we talk about engineering animals or engineering life, and when we talk, as I will in a moment, about the different animals that we have been using in order to foster our exploration of space, there's a lot of breeding that goes on there. a lot of it is pretty nasty, and that matters. So inclusion matters. All technology has multiple uses. Life is not an abstraction. And again, I believe that the way that we use words and images, tell history, imagine the future, this shapes what we actually do. So that's my setup. Just one more kind of general kind of observing thing. I think there's only one more of these kinds of slides before I get into some concrete examples. Astronomers, obviously, you know far better than I. Astronomy is just so much more remote than it once was. I still remember Frank telling me about how he was actually having to physically climb up onto the Tatelum in order to adjust it to do the initial Ozma search. Obviously, we are so far away from that now. You're also far from the observatory a lot of the time. You're just increasingly remote from your subjects in so many ways. At the same time, we have all these strategies for conceptually collapsing the distances. So we have all our wonderful illustrations of exoplanets. They are getting more and more vivid. It's more and more the kind of experience of being on the surface of those other worlds. So those two things are kind of happening at the same time. You've got this incredible rise of the virtual, but a separation from the real. Really interesting kind of tension. But then we end up with this kind of question about, well, what is it to watch from a distance? Of course, depending on who and what you're watching and why, it can be characterized in all of these different ways. It can just be observation, the way that astronomers speak of it. It can be monitoring, it can be surveillance, it can be stalking, and it can be targeting. And it all just depends on, well, what comes next. And if the watching and the future consequences are very widely separated in time, let's say by a couple generations, it's easy to kind of think that they're not connected. So just, for example, there may be some hunters in the room. If you take aim at something and you look through your sights and you press the trigger, well, that's pretty close, yes. If, on the other hand, you locate something through any kind of visualization device, let's just call it a telescope, and then 2 generations later, somebody pulls a trigger. But it's just something to be bearing in mind, again, as those distances may actually collapse, in fact. So we also have this cultural trend, which is the rise and the normalizing of surveillance. We are so used now to being monitored as well as doing the watching. But there's some brilliant critiques of this. There's one in particular, desperately trying to remember the author's name, temporarily eluding me, but anyway, her concept is surveillance capitalism, and if you Google that, you will find the book, but the Google part there, yeah. Okay, so what humans do with other life, this wide range of different kinds of behaviors, we force it to produce things for us, we profit from it, we are entertained by it, we engage in spectacles with it, putting it on stage in a wide variety of ways. Just want to flag frequently lethal entertainment, absolutely unintentionally lethal entertainment. Sometimes we actually prefer them dead over alive. There's often a high kill rate in wild harvest for luxury and prestige purposes, and kind of all of these different things. There's a lot going on, but I'm just going to jump into a couple specific examples now. Oh, one more theoretical slide, sorry. Okay, so here's the kind of basic observations. Some life with whom we've co-evolved, and I'm kind of thinking here of dogs, for example. They can do okay with us. Not always. We don't always treat dogs well. But when we have engaged in conscious creation of new relationships with other life, it tends to lose. We're using it for our purposes, which may not suit it very well. Life that we find particularly interesting, unfortunately, I think it really tends not to benefit from our attention. Life elsewhere, we've had decades of emphasis on it and this buildup, and unfortunately that means that it would be extremely interesting if it's found. And if there is other life, it's going to be kind of embedded in this really complex web of relations with us, because that's what we do. So here's kind of the proposition, sorry. If you're doing life detection work and you're hoping that everything's going to turn out just fine for that life, if it's found, and if it eventually becomes accessible, I don't think that's really logical. And if that matters, I would suggest to you that we should do more than hope. So one analogy, for example, if at the dawn of air travel, which changed everything in various kind of animal trades, what if there had also been a convention for biodiversity and animal protection at that time? we might not be staring at the incredible wave of extinctions that we are looking at right now. Those things are connected. Okay, so here are just some exemplars of some life forms we find useful or interesting on Earth, most of whom have already actually appeared in our discussions here, which is why I've chosen these ones. So the early space monkeys. So Christiansen mentioned one of them yesterday in his talk as a way of kind of making present that they had contributed considerably to the human spaceflight journey. I want to just flag a few more things though. So the one that Chris showed, a survivor, so maybe a better picture than most. But many were wild caught, some were captive bred. There were more than a few. For each one that flew that got a name, there were lots that you never hear about. There were objections even at the time, and many simply didn't make it. I think you don't need to be a primatologist to know that that is not a happy monkey. Whether or not this was necessary, I'm leaving that to the side. I'm just saying, not a happy monkey. None of the Alberts made it, so none of the ones that you're about to see, unhappy monkeys, typically drugged, restrained. Again, you do not need to be a primatologist to understand the expression on this monkey's face. So, yeah, not a happy little squirrel monkey. So that one is Gordo, didn't make it. That one is Baker. She did actually survive, but she had a very weird life. So this is Abel and Baker. Abel is the rhesus monkey. There's a big fuss at the time about emphasizing that Abel was born in captivity in the United States because they had been using an Indian-born one, and there were ethical objections because they're sacred in India. But no, we can send a captive one, and that's fine. Okay. Anyway, Abel did not make it. She was on display stuffed at the National Air and Space Museum in her capsule, but she made it back from the flight, but 4 days later died under anesthesia when they were taking electrodes out. Baker, so the little one, which is she's the focus of attention right there, the little tiny one. She's a different kind of monkey versus the larger rhesus monkey there. She did survive, but if you think this is fun for kind of a tiny monkey, I'm thinking you don't. I'm thinking you understand that this is incredibly stressful for a teeny tiny primate, even if it's sedated. And she had a pretty weird life with certificates of merit and things like that, because of course the only way to write them into the story is to call them heroes and to congratulate them for their service to America. I'm Canadian, sorry. And then of course a lifetime on display, which is also not fun for a teeny tiny primate. Or a large primate, any primate, really, basically not fun. So what I just want to flag is, when, as is so common, they are represented as heroes or as having performed a service, what's the effect of those words? And as humans talk about more and more daring human adventures in space, we are going to see a resurgence of different kinds of animal experimentation. There's plenty going on still. But how many more are going to suffer for human space travel? And so it's not just the question, though. It's also, and how are we going to tell their stories? Because if you think this is necessary, okay, fine. Just don't lie to me about it having happened. And don't tell me that she enjoyed it as a hero, right? So this is kind of just one aspect. And I flag this because all of our different space discourses kind of get muddled in together. Here's another one. I want to just take a moment and tell you why I shouldn't be showing you pictures of chimps. Because there is some recent research done, and I'm going to mention a little bit more related research shortly, that says that seeing images of chimps in human contexts actually reduces your ability to recognize that they are endangered. The two literally go hand in hand. If I show you a picture of a chimp in a human context, and I ask you later on whether you support, whether you think that they're endangered and whether or not you support conservation measures for them, there's a nasty correlation and it's not in the right direction. So please remember, chimps are in fact in danger of extinction. And that is why, as is the case for so many animal behavior experts, they spend so much of their time on conservation. Jane Goodall and her teams are not just kind of happily following around chimpanzees in the forest anymore. They are fighting for their lives. So, just wanted to mention that, but I did want to mention this as well. So kind of just following on from the space monkeys. Enos, not a happy chimp. This is a fear grin. This is an absolutely terrified chimpanzee. But what I want to just flag here. So this was a posting from the NASA History Office, 2017. Does NASA know by now? If not, why not? And if they do, is there something about the story here about us and other life and our dreams of going to other worlds that we might want to work on? So, just briefly then, humans and chimps, endangered in the wild, prognosis not good. And a lot of that is actually not just accidental habitat loss, it is intentional killing. Tons in captivity, still in labs, post-medical, biomedical sanctuaries. And I wanted to flag this one in particular because we're going to talk about unsung heroes, absolutely, completely entangled in the story of hepatitis B. We wouldn't have the vaccine without the chimpanzees as well. So, but I'm mentioning it as well because how are they made present in discussions about astrobiology and SETI? So for example, Mary Leansvold, who works with signage chimpanzees, was invited to a SETI Institute workshop. And it was because of her experience interacting with an alien intelligence. She's one of the few people that still works directly with chimpanzees who speak sign language. But you know, the reality is a huge proportion of her work is about the welfare of captive chimps. And they are survivors of biomedical research. But the entanglement there, again, is that it's from the Air Force colonies. That's the path. So these stories are all kind of entangled in together. And again, it's not a question, I'm not asking you the question here about what should or shouldn't have been done. I'm just saying what has been done and the reality of our relationships with our closest relatives. Humans and dolphins, another great example. So a part of the SETI conversation since the very beginning is an example of alien intelligence here on Earth. But the reality is they've routinely been victimized by our curiosity. So I just want to flag the work of a couple of different people here. So in contrast, for example, to what John Lilly was doing, those who work more closely with cetaceans now are very often also working for their well-being and freedom, and or choosing only to work with wild dolphins. So humans and cephalopods, another kind of tough example. A lot of our knowledge, so often held up as an example of an alien intelligence, but if you actually look at how the research has been conducted, people are starting to get around to using analgesia and anesthesia, starting. And it's not absolutely required everywhere. There's very little known really about what they need, about cephalopod welfare. So humans and homing pigeons, I'm just going to skip through a couple of different things here super quickly to kind of race to a couple of, I think, relevant conclusions. So racing pigeons, you can buy them if you wish. These are kind of your ordinary racing pigeons, $75. You can, they come in the mail, interestingly. If you want a slightly fancier pedigree, $225. But something interesting has happened in the world of homing pigeons lately. Of course, the reason that they fly is because they've been taken from their homes, and usually from their nests, and often from their babies, and that is why they rush home. This is what racing homing pigeons is all about. You know, so that fantastic ability that they have, which focuses our attention on them, then we exploit for the sake of racing. Many races, there's an extremely high lethality rate. Many of them simply don't make it home. And it's not because they just stopped and made new lives on the way. They fly to the point of exhaustion, to the point of death. But something curious has happened lately. It's just an example of the weirdnesses of what we get into with life, the kinds of trouble. So incredible inflation recently in racing pigeon, and it's due to real estate wealth in China. These things are entangled. So the world record price has just gone up. And if you think that this makes things nicer for the pigeons, we can talk about that later, but the answer is no. So it actually kind of escalates the, very, very aggressive selection. Marine fish, another kind of great example. 95% of marine ornamental fish taken from the wild. Astounding kill rate, absolutely astounding. So Finding Nemo, yeah, good luck. 5 years since it aired, actually, demand has forced some clownfish populations down by something like 75%. I'm going to skip very shortly to the end. So nature actually came up with a fungus that kills caterpillars and it sprouts out of their heads, and it came up with us, and we think this is good medicine. Some of us do. And this has literally restructured the economies of small Himalayan nations. It's one of the most kind of expensive medications kind of on the market, well, medications, some doubts about its actual effectiveness. But I just wanted to say, so spot the weird species here. So this is your test. So is it the caterpillar, is it the fungus, is it the human? I'm gonna go with the human. Such a weird kind of trouble that we are into. So here's just our few generalizations about humans, other life forms, our appreciation of their abilities and properties that leads to these webs of control, commodification, exploitation, now of course shaped by a globalized economy. Science and technology, it's recruited into these webs. These webs are entangled in all the weirdnesses of culture. We do crappy things to other life forms. Reasons ranging from the justifiable under some ethical regimes to the much less reasoned and reasonable, and the latter are not at all unusual and exceptional. I'm going to run slightly. Okay, so why would any engagement with life beyond Earth be different? Difficult access, but again, if predictions that are common within this community hold, access will begin to rapidly increase. Restricted access, but in practice, the parameters of who gets access, it's going to be those with profit motives, geopolitical and military motives, as well as curious scientists. So those are going to be complex webs into which any life out there might be entangled. Would we have some greater wisdom? I don't know. There's lots of wisdom around. There's not a lot of sign of it winning all the time. Prediction, from me, life always gets assimilated into our cultural worlds. And given time, I don't think our behavior in the solar system and beyond would be any different. I think current patterns of human behavior will reassert themselves whenever that's logically possible. And when that isn't possible, I think some people will make it, will strive to make it possible. A few different things. Why might the situation be worse for ET life? Space origin means high value. Any form of life out there has already been pre-hyped in terms of its significance, and that's on us. And that is going to drive its market value and its commodification potential through the roof, even if it's utterly unremarkable and it has no interesting characteristics whatsoever. And I think that's going to have some consequences. Could be worth more dead and in pieces than alive. Live capture and captivity would be attempted repeatedly. And again, I'm not talking about kangaroos on Mars, but even kind of small small organisms, like fish, right? The equivalent, I guess I'm saying here. We're not likely to know enough about any kind of life to know how to treat it well. Unilateral actors, I just want to flag a brilliant article by Nick Bostrom, which kind of points out that unilateral actors often go ahead with things that we kind of wish that they wouldn't. Anyway, and also life forms don't exist alone. We barely understand a lot of these webs of interdependence here on Earth. Rare means unlucky around humans. Some recent research working on these kind of dynamics for extinction kind of shows how we get there. Consumer demand threatens populations with extinction. And the rarer something is, the higher the price, which makes it that much more worth it to harvest it, which drives it that much closer to extinction. This is how it goes. People have done the math. Range contraction, if you've got habitat reduction, it enables harvesting to extinction and they're finding that the thresholds are much more concerning than they originally thought that they were. So here's one kind of real killer. This is kind of my last. Just 2 more slides after this. An animal's virtual popularity may accelerate its actual extinction. This is brutal. So some very recent research is showing that, so the most charismatic megafauna, so your giraffes, your elephants, all of these different things, they're very prevalent in the world around us. People are also very slow to recognize that they are endangered. Those things go literally hand in hand, and researchers are wondering if it's literally the high virtual population that distracts us and makes us think that they're okay. So a virtual popularity may accelerate its actual extinction, and that is bad news when we're talking about our virtual representations of other worlds. So we're looking at the paradoxical extinction of the most charismatic animals. So I'm just going to skip right here. Actually, so I do think that Earth life, if it's grown or modified in orbit or Moon, Mars, etc., sold on Earth or off Earth, it's going to have a whole lot of different values, which could be quite high. Not all of those are going to be things that most scientists would think of. So trophies in taxidermy, hunting, all of those different kinds of things, because these trends exist. Obviously, extraterrestrial life itself, if it's found, engineered combinations of Earth life and other life, I think could very well come into play as well. but our manipulations will continue and intensify. So my suggestions basically, sorry for running long, is that we should be keeping the trouble in mind. And we should remember that, we can talk about whether or not this is human nature. I regard that as a futile discussion, but this is a feature of human culture. There's trouble. And some of this could be changed. We have a little bit of a head start, but we're losing it as our region kind of expands. And so I would suggest that we should start now. And then here is my question for you then. If you personally designed, implemented, or funded a search that discovered a biosphere which might otherwise have remained undetected, and the life forms there were eventually affected negatively by predictable human actions, would you or your descendants wish you had done something differently? And if so, what? Thanks. I don't know if we've got time for questions, or did I use it all?
Yes, we have time for a quick question or two while our next speaker comes up and gets set up.
Do you think that the nature of humans is more universal, that they will take advantage of us and if we're tasty, or
I hesitate to speculate about alien characteristics. Basically, I think has to be my short answer to that. Yeah.
So that was bleak.
Yeah, sorry.
No, that's okay. One question I had was, so we are becoming more aware, and you said, as you say, there is some wisdom. Are there any examples on Earth where we got it right?
Absolutely.
I'm
Sure.
thinking about like Antarctica, how we like signed a treaty that we're all going to only like treat it nicely, but even that's not really a good analogy. So I was wondering if there was, if you had any examples of us doing it right.
Sure, there are plenty of examples of successful conservation, et cetera. The problem is, it's kind of always the same in terms of the scale of the systems that you're having to push back against. So yeah, again, I didn't kind of have time to go into the kind of the successful examples, but there's plenty of causes for inspiration.
So there's hope.
Oh, of course there's hope. There's always hope. I should have said that at the debeginning. Yes.
You dealt with the human interaction with, say, animals, etc. To me, the major problem is the human interaction with humans. For the majority of humans on the Earth, life is short, brutish, and nasty. Okay, as long as we can continue to hold the same geopolitical ideas, the expansionist ideas, the population growth ideas, the religious ideas, we're never going to solve any of the other problems.
That may be
never
true.
mentioned that at all. I mean, it's the huge growth, population growth, that is essentially causing a lot of other problems.
It's causing some of it, it's not causing all of it. Some of it is attitude, but I didn't have time to cover all of the Earth's problems in this one talk.
15 minutes late.
All right, let's take our speaker again.